Sunrise Hospital దగ్గర మేడం ఎవ్వరు లేరు, మనంతా అలా వదిలేసారు. అందుకే మేడం, అందుకనే మేడం నేను మిమ్మల్ని అనలేదు కదా ఆ రోజు. అలా కాదు, మనకి చేసేవాళ్ళు తక్కువ. లేదు మేడం, ఇప్పుడు ఎవ్వరు లేరు. ఇప్పుడు ఒక నిమిషం బిగిన్ అయ్యాక మీరు తెలుస్తుంది. అయితే రండి. నాకు అది అర్థం కాదా మేడం? చూడండి, మీరు అక్కడ చూడండి, ఒక్కళ్ళు ఉన్నారా మనకి అక్కడ? కాదు, ఒక్కళ్ళు లేరు, ల్యాప్టాప్ లేవు, ప్రింటర్స్ లేవు, అటెండెన్స్ లేదు. ఏం చేయండి, నేను ఒక్కనే చెప్పండి మేడం. రైటే మేడం, సెలవు పెడుతున్నాను అని చెప్పారు, మరి మనకి ఇక్కడ పని జరగట్లేదు కదా అంటా నేను. సరే వదిలేయండి, రండి, ఇప్పుడు ఉన్నారు కదా. ఎందుకంటే నాకు బిగిన్ అయిపోతే తర్వాత మీ ఇష్టం. మేడం
సార్ గుడ్ మార్నింగ్ ఆల్. ఒకసారి మీ ఆడిట్ ఒకసారి ఎన్ఆర్సి విశాఖపట్నం ప్లీజ్ రెస్పాండ్. ఎన్ఆర్సి విశాఖపట్నం ప్లీజ్ రెస్పాండ్.
సార్ విశాఖపట్నం రెస్పాండ్ సార్.
కాకినాడ ప్లీజ్ రెస్పాండ్. ఎన్ఆర్సి కాకినాడ. ఎన్ఆర్సి కాకినాడ ప్లీజ్ రెస్పాండ్.
NRC Kakin responding, sir. NRC Kakin responding, sir.
Okay, okay. Please respond.
Morning, sir.
Please respond.
Morning, sir.
NRC Omar, please.
Morning, sir.
సార్ వాల్యూమ్ పెంచండి, వాల్యూమ్ బాగా లోగా ఉంది.
Good morning, sir. No responding.
ఫైన్ ఫైన్. NRC Kadapa, please respond. NRC Kadapa, please respond.
Good morning, sir. Kadapa responding, sir.
Okay, madam. NRC Anantapur, please respond. Anantapur, please respond. Anantapur, please respond. Economics offline, huh? Okay. Okay. ఒక్క నిమిషం పట్టాక. NRC Peeler, please respond. NRC Peeler. Peeler, please respond. మీ నేమ్ చేంజ్ చేయండి సార్. డైలీ మీరు నేమ్ చేంజ్ చేయట్లేదు. సాయిబాబు దాసరి అని ఉంది, నేమ్ చేంజ్ చేయండి. NRC Peeler అని పెట్టండి.
Hello, can you hear me?
Yes, sir.
You can hear me, okay. Is the screen presented to you?
No, sir.
Not yet. Okay, okay. Present, how do you present the screen? Share. Is it now presented to you?
Yes, sir. Yes, sir.
But it's disappeared from my thing. Oh, God. Yeah, so is it presented to you, my screen? Hello?
Sir.
Okay,
Sir,
so
both are
should I start?
yes. 1 minute, sir. Good morning to all. I request Sri Naidu, sir, representing from NRC Visakhapatnam, to introduce our distinguished resource person, Professor R. Tandon, sir, to our participants. Thank you. NRC Visakhapatnam.
Yes, madam.
Thank you, sir.
So, good morning, sir. Good morning, my dear participants. It is with a great honor and privilege I introduce you a luminary in our field, Professor Anand sir, with a career spanning decades and a wealth of knowledge that has shaped countless minds. Professor Anand sir stands as an eminent faculty in mathematics. Their contribution to academic research and practical application have left an indelible mark. Sir did his PhD from prestigious Yale University under the guidance of 2018 able prize winner and grants, and Sir completed postdoctorate at PISR, and after a brief interlude at North East University, Sir taught at the University of Hyderabad for nearly 40 years and guided many PhD students. In his last batch, 9 PhD students acquired doctorate in 2018. One of the SAR's PhD students is currently working as a HOD of Mass Department at Andhra University. Beyond his extensive expertise, Professor Tandon sir visited University of Oregon, Institute of Advanced Studies, Princeton University, University of Sydney, and International Center for Critical Physics. After retirement, sir is extended his service at IISER Tirupati and IIT Hyderabad. As we embark on this training journey together, let us seize the opportunity to learn from one of the best in our field. Please join me in extending a warm welcome to Professor Anand sir, whose presence enriches our gathering and promises to illuminate our path towards better understanding and mastery. Thank you one and all for this wonderful opportunity.
Thank you. Okay, so shall I start? Can everybody hear me?
Yes, sir.
Yes, sir.
Yes, sir. Hear me, sir.
Can I start?
Yeah, start, sir.
Okay, so today I'll be studying two rings, the ring of integers and the ring of polynomials over a field. These are basically what I'm going to do today, but of course I'm going to look at it very number theoretically. Okay, so just for completeness, I define a field. A field is a triple Oh, incidentally, don't bother to take notes. I'll be sending the PDF file for all the notes that I'm making whilst lecturing to the coordinator, and it will be distributed to all of you. So you need not bother to write notes. Just all you have to do is to listen to me. So a field is a triple F plus dot. This is a set, and plus and dot are two binary operations. Binary operations, and such that F plus is an abelian group. Abelian group. NRC Kakinada, can he remove F plus is an abelian group with identity 0, and F minus 0 dot is an abelian group. Abelian group with identity 1, and A dot B plus C is equal to A dot B plus A dot C. So that's what a field is. So we're going to study the ring of polynomials. Now, first let's start with Z. Z has sitting inside it the set of natural numbers, and Fx has sitting inside it what I call Nx. Nx is the set of monic polynomials. Set of monic polynomials, that is, polynomials of the form xn plus a1 xn minus 1 plus so on. That is, the leading coefficient is 1. Monic means leading coefficient of 1. So the set of monic polynomials. So the only monic polynomial of degree 0 is 1. I'll make a remark. Only monic polynomial of degree 0 is 1. That's a remark. All right. So these are two big subsets of the two rings that we're going to study. Now, the first result is for Z is the division algorithm. There are many forms of the division algorithm, but okay, so this is, suppose A belongs to Z and N belongs to N. This I'll denote Zn for a natural number N, I'll denote Zn to be 0, 1, 2, up to N minus 1. That's my notation. Zn is this set. So suppose A belongs to Z, then there exists a unique R in Zn such that A minus R belongs to Nz, i.e. A minus R is divisible by N, i.e. for A in Z and N in N, there exists unique Q and R, Q in Z and R in Zn, such that A is equal to Qn plus R. So Q is called the quotient and R is called the remainder. This is the division algorithm. I'm going to give you a proof of it. Proof. First of all, a proof of existence will prove uniqueness later. Existence of Q and R. All right. So if A is equal to 0, put Q equal to 0 and R equal to 0. If N is equal to 1, then A is equal to A into 1 plus 0. 0 belongs to Zn. So we are done. So assume that N is greater than 1. If A is equal to 1, then A is equal to 0 into N plus A, and A belongs to Zn. So we are done. Assume the generalized induction hypothesis for A in N, i.e., assume that Q and R exist for all natural numbers less than A. Okay, assume this is the generalized induction hypothesis. So assume that I'm assuming now that A is a natural number, and assume that for all natural numbers less than A, Q and R exist. Q and R exist. Okay. So now I'm going to prove it for A. If A is less than N, we have A is equal to 0 into N plus A, and A belongs to Zn. If A is greater than equal to N, then N minus A is less than A. Just one minute. A minus N, sorry, this is a mistake. I knew there was something wrong here. A minus N is less than A. Then A minus N is less than equal to A. So by induction, A minus N is equal to Q1 N plus R. The R belongs to Zn. Therefore, A is equal to Q1 plus 1N plus R. So I can call this Q and I'm done. So Therefore, division algorithm is true for a whole number. That is either 0 or a natural number. So it only remains to show for a negative. If a is negative, then minus a belongs to n. So minus a is equal to q1n plus r1 for some r1 in Zn. Okay, therefore A is equal to minus Q1n minus R. Now, if R1 is 0, then we are through. And I just put minus Q1 to be Q, and R1 is 0. Then we are done. If R1 is not 0, then I write A is equal to minus Q1n minus n plus n minus R1. So this n minus R1, you call it R, and minus Q. So this is equal to minus Q1 minus 1 into n plus R. This R is in Zn, and this I call this Q. So I'm done. So therefore true for all A in Z. Okay. Then I'll also show that the fundamental theorem of arithmetic. What does that say? It says that every natural number greater than 1 is either a prime or a product of primes. Either a prime or a product of primes. A product of primes. So we're going to prove it by induction on n, but the induction will start at 2. If n is equal to 2, then n is a prime. Induction starts at 2 because n has to be greater than 1. Then assume generalized induction hypothesis. Generalized induction hypothesis, i.e., that the result is true. The result is true for all natural numbers. All natural numbers less than n. Then we will show it for n. We will show it for n. So if n is a prime, then there is nothing to prove. There is nothing to prove. Nothing. NTP means nothing to prove. If n is not a prime, then n is equal to u into v, where u is less than n and v is less than n. By induction, by induction, U is a product of primes, is a product of primes, and V is a product of primes, is a product of primes. Therefore, N equal to UV is a product of primes. There's also a uniqueness part to this, but I cannot prove the uniqueness part yet till I come to the concept of GCD. So, concept of GCD. So, let A and B belong to Z minus 0. Let the A and B be two non-zero elements of integers. Then a GCD of A and B is a natural number D such that a natural number D such that D divides A and D divides B, and if C divides A and C divides B, then C divides D. So it's common divisor of A and B, and amongst the common divisors, it's maximum. All other common divisors must divide it. That's a GCD. Now, I'm not saying that GCD exists. GCD may not exist, but I'll prove that it exists. So let S be equal to the set AU plus BV, where U and V and U belong to Z. Let S be equal to A, or all numbers of the form AU plus BV, where U and V belong to Z. For those amongst you who are familiar with ring theory, this is the ideal generated by A and B in Z. But I don't want to use any ring theory, so I'll just leave the definition as that. Notice that A and B belong to S. Why? Because A is equal to A into 1 plus B into 0, and B is equal to A into 0 plus B into 1. Right? Should I write it down? A is equal to A into 1 plus B into 0, and B is equal to A into 0 plus B into 1. So A and B belong to S. Also, I notice that A squared plus B squared belongs to S, because I can put U to be A and V to be B. I can put U to be A and V to be B, so A squared plus B squared. Therefore, A squared plus B squared is a natural number. So therefore, N intersection S is non-empty. N intersection S is non-empty. So let D be the least natural number in S. Let D be the least natural number in S. Now, I make two observations. The difference of two elements of S is in S. Right? If I have some element AU1 plus BV1, another element AU2 plus BV2, then the difference will be A of U1 minus U2 plus B into V1 minus V2, which is again in S. It's an integral combination of A and B. So that is one observation. Second observation is an integral multiple of any element of S is in S. Right? So if I have some AU plus BV in S and I multiply across by T, I'll get AUT plus BVT, which is again an integral combination of A and B. So this is also true. So now, so 2 implies that dz is in S, right? Because d is the least natural number in S. So d is in S, and an integral multiple of any element of S is again in S. So dz is in S. Now I want to show the other way around. I want to show that S is contained in dz. So let little s belong to capital S, and by division algorithm, S is equal to dq plus R. The R belongs to ZD. I'm dividing S by D, and D is a natural number, and I get a quotient and a remainder. Remainder is in ZD. That is, it is less than D. It's a natural number less than D or 0. So then R is equal to S minus DQ, which belongs to S. Why? Because of 1 and 2. This is the difference of 2 elements of S, and therefore it is again in S. But D is the smallest but R is less than D, and D is the smallest natural number in S. Therefore, R is not a natural number. Therefore, R is equal to 0. The only natural number, the only non-natural number in ZD is 0. The only non-natural number in ZD is 0, so R must be 0. Therefore, S belongs to dz. Therefore, S is equal to dz. Now, my claim is that D is D is a GCD of A and B. Okay, so since A and B belong to S, which is equal to dz, therefore D divides A and D divides B. And since D belongs to S, therefore D is equal to AU1 plus BB1 for some integers U1 and V1. So let C divide A and C divide B. This implies that A is equal to C into A1 and B is equal to C into B1. When I substitute, I get T is equal to C into A1 U1 plus C into B1 B1, which is equal to C into A1 U1 plus B1 B1. Therefore, C divides T. So, and then uniqueness is easy. Suppose D1 and D2 are GCDs of A and B, then by the properties, D1 divides D2 and D2 divides D1, and both are natural numbers. Therefore, D1 is equal to D2. Existence of, so I have the existence of GCD of any two natural numbers, and I have also proved the uniqueness, because for me, the GCD is a natural number. I'm not allowing negatives to be GCDs by my definition. So, so that's why I get uniqueness. Otherwise, I'll get Tn minus T, which I don't want. Okay. Yeah. So from this, I get a small proposition. Suppose A divides BC and the GCD, this is my notation for GCD, brackets, GCD of A and B is 1. Then A divides C. Then A divides C. So let us prove that. GCD of A and B is 1 implies that 1 is equal to AU plus BB for some U and V in Z. This implies that C is equal to AUC plus BCV. I've just multiplied across by C. So next page. And BC is equal to some A into X, because A divides BC. So BC will be A into X. So this is equal to AUC plus AXV. That is equal to A into UC plus XV. Therefore, A divides. I'm just going to give an exercise over here. Exercise. Use this to show that factorization of a natural number is unique, except for order. Except for order. Because it is multiplication is abelian, or you will have to take allowance for order, because if I change the order of the primes around, it will not make a difference to the product because of abelianness. So I have to make an exception for order. The order of the primes, except for order of primes. All right. So let me introduce some notation. I'll say that A is congruent to B mod n if n divides A minus B, i.e. A minus B belongs to NZ. So notation, when you say that A is congruent, you write A is congruent to B mod n. Okay. All right. I haven't come to FX yet, but I have one more thing to say about this. I want to ask a question. Is there a finite set? Is there a finite set with, say, n elements, which looks like Q, which looks like Z algebraic, i.e. is a commutative ring, with one. Does such a finite set exist? Then the remark, if there exists such a set, say S1 plus 1 dot 1, then we can define addition and multiplication on any set with n elements, so that the set becomes a commutative ring with unity. Commutative ring with one. How can I do that? Suppose S2 is any other set with n elements. So S1 and S2 have the same number of elements, so I can let F from S2 to S1 be a bijection. Right? The two sets have the same cardinality, so I can get a bijection between them. F from S2 to S1. Now define plus 2 and dot 2 on S2 by as follows. By U plus 2V. So U and V are in S2. I define this to be, so take FU plus 1 FP, add them up and take F inverse of that. Because F is a bijection, F inverse exists. You can define U like that, and similarly U dot 2V as F inverse of FU dot 1 FV. then you can see that uh, then S2 plus 2 dot 2 is isomorphic under F to S1 plus 1 dot 1 and so is also a commutative ring with 1. Commutative ring with 1. So whatever properties S1 will have, S2 will also have. So actually the set does not matter. If on one set with n elements, I can define an addition and multiplication so that it becomes a commutative ring with unity, then on any set with n elements, I can do it by this method. So then we take my S to be Zn, which is, recall, it's 1 up to n minus 1. Now the advantage of taking, this is a set with n elements. Now the advantage of taking Zn is that I have a plus and dot. I can add two elements because Zn is contained in Z. I can add and multiply elements, but addition and multiplication are not binary operations of Zn because the sum of two elements of Zn could fall outside Zn and the product of two elements of Zn could fall outside Zn. So plus and dot are not binary operations on Zn. So I define I'm going to define a new operation for A, B, and Zn. A plus n B, this is addition modulo n, to be the unique element of Zn obtained by dividing A plus B by n. So, i.e., A plus n B is the unique element of Zn such that A plus B minus A plus NB belongs to NZ, i.e., A plus B is congruent to A plus NB mod n. Similarly, define, this is addition modulo n. A dot n b, this is multiplication modulo n, to be the unique element of Zn congruent to AB mod n. So AB is congruent to A dot NB mod n. Then you can check, I'm not going to do it, Zn plus n dot n is a commutative ring with 1. The 0 is see 0 is in Zn, so that's going to be the 0 with respect to plus n. And one is again in Zn. I should remark, take S to be, let n be greater than 1. For all this, n is greater than 1. Z1 is just a single to 0, so it's not a commutative ring with unity. There's no unity. So Zn is a commutative ring with 1. Yeah, so my question is, see, Z has only two multiplicatively invertible elements, namely plus or minus 1. Z has only two multiplicatively invertible elements. With plus or minus 1. The question is, what are the multiplicatively invertible elements of Zn? Question. What elements of Zn are multiplicatively invertible with respect to dot n, that is multiplication modulo n. What elements of Zn are multiplicatively invertible with respect to dot n? So suppose, and I'm going to try to answer this question. Suppose, of course, 0 into anything is 0, so 0 can we have to exclude 0. Suppose A has a multiplicative inverse P, i.e. A dot NB is 1. This implies that AB minus 1 belongs to NZ, i.e. AB is equal to Qn plus 1. This implies that the GCD of A and N must be 1. Because if R divides A and R also divides N, then from this equation, AB is equal to Qn plus 1, we will see that R will divide 1. Because if R divides A and R divides N, then from star, I'll call this star, from star, R divides 1. So the GCD of A and N must be 1. So therefore, this is a necessary condition. Therefore, for A to have a multiplicative inverse with respect to dot n, a necessary condition is GCD of A and N is 1. So now the natural question to ask is it also sufficient? So suppose GCD of A and N is 1. This implies there exists U and B in Z such that AU plus NV is 1. Right? Now, U, by division algorithm, by division algorithm, U is equal to Qn plus R, where R belongs to Zn. So I substitute for U, I get A into Qn plus R plus NV is equal to 1. That means A into R plus N into AQ plus V is equal to 1. Therefore, AR is congruent to 1 mod N. Therefore, A dot NR is 1. So therefore A has an inverse, i.e. R is the inverse of A. So it's a necessary and sufficient. Therefore, a necessary and sufficient condition for 1054. I still have a necessary and sufficient condition for A belonging to Zn minus 0 to have a inverse with respect to dot n, that is multiplication modulo n, is that the GCD of A and N must be 1. So I'll call Zn cross to be all multiplicatively invertible elements of Zn, and that is equal to set of A in Zn minus 0 such that the GCD of A and N is 1. And I'll call the cardinality of this set phi n. Definition. Phi n is equal to the cardinality of Zn cross. Incidentally, if n is equal to p a prime, then IP is equal to 1 for I equal to 0, 1 to up to p minus 1. Therefore, ZP cross is equal to 1 to up to p minus 1, which is equal to ZP minus 0. Therefore, ZP plus P dot P is a field. So I have a finite field with P elements. Let me make a definition. If F is a finite field, then the order of 1 by that is the multiplicative inverse, with respect to addition, addition is called the characteristic of the field. The characteristic of the field. Right, one is the identity with respect to multiplication, but there is another operation, addition. One is not the identity with respect to addition. Zero is the identity with respect to addition. But because the field is finite, F plus is a finite group, so one will have some finite order. That order is called the characteristic of the field. And my claim is that the characteristic must be a prime. Characteristic is a prime. Here I'm going to use the fact that a field has no zero divisors. I'm not going to prove that because I think that's easy to see. So if n is equal to the characteristic of F and n is equal to uv, then n into 1 is 0. Okay? Because n is the order of 1. But by this I mean 1 plus 1 plus 1 n times. 1 plus 1 plus 1 n times. N times is 0. Okay? Now, by distributive law, you can see that 1 plus 1 plus 1 u times into 1 plus 1 plus 1 v times. By distributive law, this is equal to 1 plus 1 plus 1 uv times, that is n times, which is equal to 0. So P1, sorry, I made a mistake. U1 so U1 into V1 is equal to 0. And the order of an element is the smallest, right? N is smallest such that if you add 1 plus 1 plus 1 n times, you get 0, right? It's the order and addition. Please remember that. The characteristic is the order and addition of 1 under addition. So n is, so by minimality of n, we have a contradiction. If u is less than n and v is less than n. Because I'm going to get 0 divisors now. So therefore, n must be a prime. So you can see that the order of 1 in ZP is P. So the characteristic now, if characteristic of F is P, then if I take PA for any A belongs to F, any, this is equal to A plus A P times. This is equal to, by distributive law, A into 1 plus 1 plus 1 P times is equal to A into 0 is equal to 0. So I'm going to get P of A will be 0 for all A in F. So, okay, so therefore, if I take A plus P to the power of P in F, this will be equal to by A to the P plus PC1, A to the P minus 1, P plus etc. plus B to the P. You'll see that all the PCIs are divisible by P, And so all the middle terms will become 0, and this will become A to the P plus B to the P. All right. I haven't looked at FX yet, but let me go to the Chinese remainder theorem. Chinese remainder theorem. I'm trying to finish off Z and then go to polynomial rings. Chinese remainder theorem. So what the Chinese remainder theorem says is following. Let M1, M2, MR be natural numbers. Actually, they can be non-zero integers as well, but it doesn't matter. Natural numbers which are mutually coprime, which are mutually coprime, i.e., Mi, Mj is GCD is 1 for all Ij, I not equal to j. So let's suppose I have R mutually coprime natural numbers. Let A1, A2, AR be arbitrary integers. Okay, just any old integers, A1 to AR, R of them. Then there exists X in Z such that X is congruent to AI mod M. I from 1 to 1. So that's the statement of the Chinese remainder theorem. I can find a single X which is congruent to each one of the AI's modulo Mi. A single X. Okay, so proof. The proof is going to be by induction on R, proof. But the induction will start not with R equal to 1 because it makes no sense. The induction will start with R equal to 2. R equal to 2. So suppose R is equal to 2. So I have only two, M1 and M2. We have just two, M1 and M2. That's all. And then I have, of course, A1 and A2. Now, GCD of M1, M2 equal to 1 implies there exists U, V in Z such that M1U plus M2V is equal to 1. Then let X, it's quite easy, let X be equal to M1U A2 plus M2V A1. Okay, to take X to be M1U A2 plus M2V A1. Then X minus A1 is equal to M1U A2 plus M2V minus 1 A1, which is equal to M2V minus 1 is equal to minus M1U. So this is M1U A2 minus M1U A1. Let me call this star by star. M2V minus 1 is equal to minus M1. So this belongs to M1Z. And similarly, X minus A2 belongs to M2. i.e. X is congruent to A1 mod M1 and X is congruent to A2 mod M2. So for R equal to 2, the result is proved. It's really quite trivial. I mean, it's very easy to construct my X. Just you get it. Because GCD of M1 and M2 is 1, there exists U and V such that M1U plus M2V is 1. And then you just take X to be M1U A2 plus M2V A1. That's it. And it's done. Now for general R. Assume the result is true for R minus 1. Then there exists a Y such that Y is congruent to AI mod Mi, I from 1 to up to R minus 1. By the case R equal to 2, there exists an X in Z such that there exists a Y in Z such that X is congruent to Y modulo M1, M2 into MR minus 1. I'm taking the product of this, and X is congruent to AR modulo MR. Okay, so now I have just two numbers, M1, M2, MR, minus 1, and MR, and these two are mutually co-prime because the MIs are mutually co-prime. So now I have X minus I from 1 to R minus 1. X minus AI is equal to X minus Y plus Y minus AI. And X minus Y belongs to M1 into M2 into MR minus 1Z. And Y minus AI belongs to MI Z. And this is contained in MIZ. So therefore, X minus AI belongs to MIZ. I from 1 to R1. So we're done. We are done. So that proves the Chinese remainder. There is a very important application of this. So define, let n be a natural number, n greater than 1. Define a map In from Zn by x going to the remainder when x is divided by n. So Inx Inx is equal to the remainder when x is divided by n. Then so I have a map, In is a map from Z plus dot to Zn plus n dot n. My claim is that In is a ring homomorphism. In is a ring homomorphism, i.e. Rn of O, I called it In, it should be Rn. R stands for remainder. I'm sorry, it should be Rn. Correction, it replace In by Rn. So Rn of A plus B is equal to Rn A plus n Rn B, and similarly for multiplication. So let us show. I know that A plus B minus Rn of A plus B. This is the remainder when A plus B is divided by n. So this belongs to nz. Then I also know that A minus Rna belongs to nz. I also know that B minus Rnb belongs to nz. And finally, I know that Rn A plus Rn B minus Rn A plus n Rn B belongs to nz. Right? Because this is the remainder when Rn A plus Rn B is divided by n. So now, let me look at A plus B minus R and A plus N R and B. This is equal to A plus B minus R and A plus B plus R and A plus B. No, please, I have an easier way to write this, so I'm going to slightly change this. Sorry for this. Yeah, this is equal to RNA plus some Q1N, because A minus RNA belongs to NZ, plus RNB plus some Q21, because B minus RNB belongs to this. Now RNA plus RNB, this is equal to RNA plus N, RNB. I'm looking at RNA plus RNB, and I'm looking at the third thing over here. This is RNA plus some Q3N plus Q1N plus Q2N. So this is some multiple of N. Therefore, A plus B minus RNA plus N RNB belongs to NZ. And therefore, RNA plus B is equal to RNA plus N RNB. I'm going to leave it to you to show, it's a very good exercise, show that Rn of AB is equal to RNA dot N RNB. So this is a ring homomorphism. But something even better is true. Suppose T is any natural number. Suppose T belongs to N, then, and suppose I look at Z and T. This sits inside Z. So I can restrict this Rn. It's defined on the whole of Z. I can restrict it to Z and T. And I get a map from this to Zn. Now please note, though Zn T is a subset of Z, but Znt plus Nt dot Nt is not a subring of Z. See, for a subring, you must have with respect to the same operations, whereas plus and plus Nt are not the same, dot and dot Nt are not the same. However, I claim that Rn as a map from Z and T plus Nt dot Nt. What does this mean? Addition modulo Nt and multiplication modulo Nt. 2 Zn plus N dot N. This is a ring homomorph. I.e. Rn of A plus Nt V is equal to Rn of A plus N of Rn of B. And similarly for multiplication. Similarly for multiplication, I have Rn of A dot Nt V is equal to Rn of A dot N of Rn. I'm not going to prove this. Should any of you require help, it's a routine thing. Should any of you require, because I'm running short of time, I have only 5 minutes. So let's assume this. Now, look at Chinese remainder theorem for R equal to 2. Look at the Chinese remainder theorem for R equal to 2. So I have M1 and M2 mutually co-prime. And arbitrary A1 and A2. And I can find an X such that X is congruent to AI mod Mi. Now, suppose I divide X by M1, M2. Let Y be the remainder if X is divided by M1, M2. Therefore, Y belongs to Z of M1, M2. It's between 0 and M1, M2. Let Y be the remainder. So then, Y minus AI is equal to Y minus X plus X minus AI. Y minus X belongs to M1, M2, Z. It's divisible by M1, M2. And X minus AI belongs to MI, Z. and this is contained in MIZ. Therefore, Y minus AI belongs to MIZ for I1 and 2. Now, for Y minus, so therefore, I've strengthened the Chinese remainder theorem. There exists a Y in Z of M1, M2 such that Y minus AI belongs to MIZ, is divisible by MI, I from 1 to 2, I1. So I strengthened it. I found an integer in a smaller range, namely Z of M1, M2. So now look at the map. Suppose, look at the map from Z of M1, M2 to Z of M1 cross Z of M2. If I have any A1, A2 here, what is the map? Oh, sorry, I forgotten to write what the map is. Look at the map. R look at the map R X going to RM1X, RM2X. That is the remainder when X is divided by M1 and the remainder when X is divided by M2. So if A1 and A2 belongs to Z M1 cross ZM2, then the Chinese remainder theorem tells us that there exists an X in ZM1 M2 such that RM1X is A1 and RM2X is A2, i.e. R is surjective, i.e. R is surjective. Now, both these sets, left-hand side, the cardinality of ZM1, M2 is M1, M2. And the cardinality of ZM1 cross ZM2 is equal to the cardinality of ZM1 into the cardinality of ZM2, which is equal to M1, M2. So both both domain and range have the same cardinality, but a surjective map between two finite sets of the same cardinality is automatically injective. This follows from the pigeonhole principle. Is automatically injective. Therefore, R is an isomorphism of rings. Therefore, the invertible elements in ZM1, M2 i.e. ZM1, M2 cross correspond, map to the invertible elements of ZM1 cross ZM. That is ZM1 cross ZM2 cross. But cardinality of ZM1, M2 cross is phi of M1, M2 by definition. And cardinality of ZM1 cross is phi M1. And cardinality of ZM2 cross is phi M2. Therefore, if M1, M2 is 1, this Chinese remainder theorem I've used, so I have to have this condition. Then phi of M1, M2 is equal to phi M1 to phi M2. I'll stop here. So the major result that the Euler phi function for two natural numbers which are mutually co-prime is just the product of the Euler phi functions of each natural number. I will need this later on for my. I'd be happy to answer any questions, but this is a good place to stop with this result. This has come as a consequence of Chinese remainder theorem. Any questions? Somebody come in. So I have not managed to look at polynomial rings. I will do that next time. But the theory for polynomial rings is very similar to what is going on over here for Z. Z plus dot and Fx plus dot are very, very similar rings. I was supposed to do Lagrange's theorem for polynomials in today's lecture. I will do it the first thing in the next lecture. I've not had time, but it's just a consequence of this homomorphism Rn. Questions? Any questions?
Good morning,
Good morning.
sir. Determinant term has some applications in computer science and number theory. So I want how to apply.
I can't hear you. Can you?
how do we apply digital algorithm in coding of numbers, that is in cryptography? So please tell me, sir.
No, I couldn't hear you. I can't make out what you're saying.
How do we apply digital algorithm in cryptography?
How do I apply? After that, I can't get.
Division algorithm in cryptography. Cryptography, sir. Coding of numbers.
In
Coding of numbers.
coding, cryptography.
Yes, sir. In cryptography.
Oh, that is that's a big answer. I mean, look, you see, you use the following fact. The following fact is very crucial in applying number theory to cryptography. And this is the fact. Given two numbers, natural numbers, if you feed it into a computer, the computer will multiply it trivially. Very easily it will multiply it. But if you give the product of two numbers to the computer and ask it to find the two factors, suppose you have two primes and you feed the primes into the computer and ask the computer to multiply it, within seconds, fractions of seconds, it will multiply them. Even very large primes. I mean, even if I have 200-digit primes, it will multiply them in a very short amount of time. But suppose you have the product P1, P2, you know the product, and you feed it into the computer and ask the computer to find the factors P1 and P2, it will not be able to do it in a short time. In fact, it may not be able to do it at all. You would be surprised, but there are things which computers find it difficult to do. So, I mean, so you exploit this fact to get a code, but to do that would take, to tell you how to do it would take me at least 15 minutes. So we don't have 15 minutes just now, you have another class. So, but that is basically what is exploited to get a crypto system. That's the basic idea that is exploited to get a crypto system, because your crypto system should not be breakable by a computer. And this is the thing that you exploit, that multiplication is easy, but factorization is difficult. The mathematical way of saying this is that there is no polynomial time algorithm for factorization. A polynomial, you can take it to mean a polynomial time algorithm is an algorithm which a computer can use and perform in a reasonable amount of time. I mean, if a computer is going to take 10 years to factorize, that's not a reasonable amount of time. I mean, by that time, your code, breaking the code will become infructuous. So there's a formal definition for polynomial time algorithm, and we exploit the fact that there is no polynomial time algorithm for factorization for computers. So, but to give you a crypto system using that will take me at least 15 minutes to half an hour. So I'm not going to attempt it.
Thank you.
But yes, you can use it. You can use it to get crypto systems.
Thank you, sir. Thank you, sir.
But that's not in the syllabus. So, in fact, last semester I taught a course at IIT precisely explaining how number systems and elliptic curves can be used to set up crypto systems, but that's a totally different course. That's a totally different course. Any other question? Any question concerning what I have told you? I'll be sending the PDF file for these notes to the coordinator, and you can go through it. And in the next lecture, after going through it, you can ask me questions about what I have done. Okay? So I think we'll close the session now. Any question? I can't hear anything.
I'm not asking any questions, sir. Thank you,
Okay.
sir. Session
Okay.
complete.
So I'll log out now.
Yes, sir.
I'll log out. Thanks.
Thank you, sir. All the analysis, please join within 5 minutes as Abhay is waiting for us. He already joined.
Madam, can I just test whether I can share and everything before starting?
Sir, can you hear us?
Shall we test whether I can share and can you hear me?
Yes, sir.
Okay,
Sir,
I
you
will
can
try
test.
to share this.
You can.
Yeah,
Now
yeah.
you are the presenter. Please
Okay,
share
just
any PPT.
yeah. Okay, so can you see this?
Sir, it is visible, sir.
Okay, fine. Thanks.
Okay, sir. Thank you.
It's visible, sir.
Sorry.
Visible, sir.
Okay, yeah.
Sir, all will join within 5 minutes. Please bear with us. Just
Yeah, yeah, no
5
problem. Yeah, no problem.
times. Madhavi, madam. Is it audible? వినిపించండి. సార్ ఆడిబులేనా? నాగేంద్ర సార్ వినిపిస్తుందా? క్లారిటీ ఉందా మాట్లాడుతుంటే? సార్ నాగేంద్ర సార్ క్లారిటీ ఉంది కదా?
వినిపిస్తుంది సార్.
శ్యామ్ గారు చాతుడు కాలర్ మైక్ కాలర్ మైక్
లలిత మేడం
సరే సరే
ఆడిబులా మేడం? మేడం వినిపిస్తుందా మేడం? వినిపిస్తుంది. మేడం ఒక్క 2 minutes మేడం. ఓకే ఓకేనా మేడం?
ఇండియా ఆఫీస్
Good morning to all. I request Dr. S. Lalita Madam, representing NRC Kadapa, to introduce our esteemed resource person, Dr. Abhay Somal sir, to our participants. Thank you, ma'am.
A very good morning to everyone. I am Dr. S. Lalita, GDC Nandyala. It is my great pleasure to introduce Dr. Abhay Soman sir, Assistant Professor at University of Hyderabad. His education, he did MSc from IIT Kanpur, PhD from IIT Bombay under the guidance of R. Preeti ma'am. Academic positions, Assistant Professor in the School of Mathematics and Statistics, University of Hyderabad, Visiting Professor at IIT Bhilai, Research Associate at UMDAE Center for Excellence in Basic Sciences, Mumbai, Visiting Scientist at Indian Statistical Institute, Bangalore, under the mentorship of B. Suri sir, National Postdoctoral Fellowship at IISER Mohali under the mentorship of Amit Kulshrestha sir, research interest, principal algebra with involutions, Galois homology and algebraic groups, publications, totally positive field extensions, and the Pythagorean Index Journal of Algebra and its applications. And triviality of the reduced Whitehead book over Hensling Fields Math Journal, and adjacent groups or cubics and R equivalents in Proceedings of American Mathematical Society, and adjacent groups or cubics and R equivalents in Journal of Pure Applied Algebra, an expository article, Medelberg Factorization Theorem and Value Division Algebras for the Mathematics Students, Volume 88, and his teaching subject is Commutative Algebra. I once again welcome Sir Dr. Abhay Soman sir, and also I thank the Commissioner of College Education for giving me this opportunity. Thank you, madam.
Okay. Thank you. Thanks a lot for this kind introduction. And I think some of you, I think I have met. So it's good to have known people in the audience. So let me know when shall I start? Yeah.
Sir, you can start, sir.
Okay, sure. Yeah.
Thank you, sir.
Yeah.
Please start the session.
Okay. So I will be talking about maximal ideals and prime ideals. But before that, just to fix the notation, so let me begin with definition of ring. Okay, so the ring, I'm sure that you all are familiar, but only thing what I'm going to assume is a ring with unity, right? So I will just quickly write down the hypothesis. So of course we have ring means you have a two binary operations given on the set R, where plus is with respect to plus. Usually that's how we write. It's an abelian group. Okay, so with respect to, just wait a minute. Yeah, it's an abelian group, right? And then there is another operation we usually call dot. With respect to it's a monoid. So what is a monoid? Well, basically it's the associativity is guaranteed. Okay, this is same as this. And I want to say that's where the unity comes into picture. There is a one multiplicative identity such that this is equal to this. Okay, this is for all R, S and T belongs to R. Okay, so these two things, and of course we have two different operation on the same set. Then there should be they should be compatible. Okay, what I mean, with the condition that if I have R, then I suppose first add two elements and then multiply with R. I will get the same result if I multiply R with S and then with R with T. Okay, and similarly on the right also, if I multiply like this, then I will get the same result. Okay, so some of the books actually may not require you that ring should have a unity. However, throughout I will be using ring with unity. Then let me give some examples. The one I will be mostly dealing with. So let me give. So the first one, let's say, is familiar one. So Z mod NZ, right? So this is as a group. We usually write it as right 0, 1, so on so forth, and up to n minus 1, right? So group, you already know this is an abelian group. The multiplication is usual. If I have two elements I and j in this ring, then of course I know how to multiply. Namely, I define this into this. Basically, this is the notation for definition. Okay, this I define to be I into z. So so what are these bracketed 0, 1, 2? These are the remainder after you divide uh, any integer, right? So that is the thing. So another one, very familiar one, is the matrices over, let's say, field f. Okay, so what are those? Well, these are typically written as aij, correct, where aij are elements from f, and you have one I less equal n, one I j less equal n, right? So these are the matrices. Now, which is another example which is very similar. In fact, there is a so-called isomorphism is another one. So namely, for that, let's say I have a v be a finite dimensional vector space, let's say over R. It can be over any field actually, but let's say even here also I will put R just to be concrete. Okay, so finite dimensional vector space, and then I consider this. What are these? So these are the, by definition, these are the linear maps from V to V such that T is R linear. Okay, so this is R linear, and you can have an operation. Let's say T1 and T2 are elements of this. This is called the endomorphism. Okay, this is again R endomorphism ring. Then of course you know how to add them. So this should be a linear map from V to V. So therefore, this evaluated at V we define to be T1 of V plus T2 of V, of course. So this makes abelian group because V is a vector space. So this addition, this is done in V. Okay, so V plus. So same addition essentially we use, and then we need to define the multiplication. So that is the composition. That's what we define. Okay, so basically this is T1 of T2 of V. Right, so you can see that with respect to this, this will become ring with unity, and of course the identity map. So we denote like this. V, well, it's by definition maps to V, right? So with respect to this thing, we have, and of course you can, of course you know that in general, given T1 and T2, right, they may not, so T1 compose with T2 may not be same as T2 compose with T1. Okay, so that's what makes them interesting. Okay, so now another example I want to give is the polynomial ring. So again, let me work with okay, R, let's say Rx. Okay, so this is polynomial ring in one variable over real numbers. Okay, so this is this is the thing I think you know. So typical element is of the form summation ai x to the power I running from 1 to n, and ai are of course called coefficients. They are from R, and n can be any natural number, right? Now you know how to add two polynomials, correct? We just okay. So basically, if I have polynomial, let's say I running from 1 to n1, ai x to the power I plus summation. Let's say I have polynomial I running from 1 to n2. It can be a different n2, say bi x to the power I. Then of course you know that we have to take the first coefficient, right? So how do you do that? Then you can say that this is b n2 x to the power n2 plus something. When this will happen, when n2 is actually strictly bigger than n1. Similarly, have this one x to the power n1 plus rest of the terms. The leading, the highest power term will be an1 plus bn2, and to the power n1 when n1 and n are same, right? Plus something, yeah. So therefore this is a basis of the polynomial ring over R. It is infinite dimensional, that is okay, but anything by the very construction, anything you write it as a linear combination of this thing. Now I want to generalize this to polynomial ring in several variable, but as of now let us just take in xy. So this I want to write it as Rx with y. So what does it mean? So let me write it. So this is actually means that it is summation I running from 1 to n. Now this ai x times y to the power I, where now ai x, these are the polynomial over R. Okay, then and n is of course some natural number. Okay, union with 0. Actually I can have 0 here also, above also, because yeah, I can have 0 because the constant term. Okay, so look at the new ring, that is rxy, rxy. So basically we are saying, okay, the coefficients are from the ring Rx, and then you attach the variable. Okay, so for instance, I can have x plus x square plus 1, right, times y. This is a part of the Rxy. Similarly, I can have let's say arbitrary element a0, a1 plus a1x, let's say, so on an x to the power n. I can have this plus y to the power r for some r I can have, and then the linear combination of these things. Okay, okay, is this clear? This rxy, I'm going to use it. So is there any question or comments as of now? Okay, all right. So similarly, actually, you can construct similar terms. You can construct, let's say, R x1, then x2, so x3, so on, so forth, xn. It's kind of inductive. What does it mean? Already you know, if I have two variables, how to do it. So basically, this I will construct as, okay, polynomial ring x1, x2, so on x3, sorry, xn minus 1, okay, this over xn. Now you know how to construct r x1, x2, xn, right? Because this will be x1, x2, so on so forth, xn minus 2, then xn minus 1, right? And then xn, and so on so forth. Okay, so just to give this will be in general will of the form summation over a I1, I2, so on, In. Okay, these are the coefficient from real numbers, and then x1, I1, x2, I2, xn, In. So this sum is finite. Okay, the finite sum. So in algebra, we don't work with infinite sum because it's very difficult to get convergence and so on. Okay, so these are the elements from real numbers. Okay, and yeah, this is a finite sum. So let's go back again to the one in two variables just to make sure. So for instance, I can have elements of this font, right? A0. Let's just take the example above. In general, it will look like this one, correct? But however, I can use the usual operations for polynomial ring, the whatever intuitive operation you have known, x to the power y power. Now you can see that now the coefficients just above a0, for instance, there is no coefficient of x, so I1, I2, In, so they can be natural number or 0, right? So they can be, so here so same thing, this thing I can write in this form. So that's what. Okay, fine. Now another thing, so these are some examples. Of course you can give several examples, but let's immediately go to the definition of ideal. Okay, definition of ideal. All right, so let R be a ring. Let R be a ring. Okay, and so left. Okay, so left ideal, left ideal I of R is, first of all, the ideal must be a subgroup under addition. Subgroup and of R plus. Okay, so it should be an, of course it is a subgroup of an abelian group because R with addition is abelian, right? So therefore it should be a subgroup. And next one is that given any R in R and let's say X in I, we must have R times X in I. Okay, so this is called a left ideal. So what it says, again, to give the analogy, okay, so remark maybe, I'm sure that everyone has seen this, so the remark is more useful, I should say, because this in terms of what you can, I will write it. So ideal of R can be thought as or can be thought in similar way as subspace of a vector space. Okay, just quickly recall, you have a vector space. Okay, just I will just simply write it here. Say V is a vector space. Okay, vector space over let's say R over field. In fact, now I want to say something. W is a subspace of V. What does it mean? Can anyone tell me? Okay, remember what is a subspace? Namely that first of all, yeah, W plus, right? This is a subgroup again. And the same thing for the first condition, and the same thing happens, but here instead of R you have alpha from R, and let's say W from capital W. Alpha dot W should be again in W, right? That's the subspace. So therefore you want to consider ideal. Let's stick with the left ideal. You want to consider the left ideal, then first of all it should be a subgroup. Okay, moreover, I begin with any element of ring, given ring, and any element of given set X, right? Then the multiplication should again be in I. So very similar to the vector space. So instead of filled, you work with arbitrary rings. So that's the beauty of it. So, okay, by the way, the exactly same thing you can work with something called right ideal. So the first condition stays as it is, but respectively instead of x times, instead of the left multiplication you just consider the right multiplication. Okay, yeah. So this is this one, and this remark actually you can think in terms, so it becomes linear algebra actually. In fact, the theory of ideal can be thought in terms of the linear algebra. We'll see actually that also. Okay, any question as of now? Okay, so let me give examples. Before that, okay, I think I haven't defined, but I am sure that you all know uh, um, what is definition of commutative ring. Okay, so a ring always with unity, a ring with unity is called, let's say ring A with unity is called commutative if, okay, if for any A and B in A, we have AB, the multiplication must be same as BA. So whenever there is a commutative ring, I usually denote by A, B, and so on. Okay. So in commutative ring, so this is a remark, very easy to see. Okay. In a commutative ring, every left ideal is a right ideal. Yeah, this is just because of commutative, and vice versa. Of course, every right ideal is every right ideal is again a left ideal, right? So okay, fine. So this is a commutative ring. So let us give examples. So I will begin with polynomial ring. Again, the point to consider polynomial ring is actually very very geometric. You can have a geometry uh, related to polynomial ring. Okay, that's why we consider it. So let's begin with, let's say, Rx. Okay, suppose this is our ring. So okay, wait, I will denote it by A. So recall that Rx is commutative. Okay, so there is no issue of left and right ideals here. Okay, so you can just begin with anything. If it is ideal, then yeah. Okay, so uh, let me give one example. Let's say I1 to be some, okay, yeah, summation ai x to the power I running from 1 to n. Okay, ai is r. consider this set. Now look at the set. This is from I running from 1 to n, and of course n is in any natural number. So typical element is of this form: a1x plus a2x square, so on with an x to the power n. So there is no constant term. Right, there is no constant term in the I1 whatever. Now you can see that easily that I1 is in fact a subgroup. I1 under addition is a subgroup of A under addition, because as you can see, if I have a two polynomial, there is no constant term. If I add them, then of course there is no constant term, right? So that is the case. And furthermore, if I have any polynomial f in A, and let's say I have another polynomial px in I1, then f of x times px. Now this is a new polynomial, okay? And this new polynomial, how does it look like? Okay, so just let's say I have a polynomial which is anything, z running from, let's say, 0 to m, bz x to the power j. This is f, particular f, and I have a polynomial px, let's say I running from I running from 1 to n, then ai x to the power I. Okay, now how do you multiply? Well, I have, right, you have j running from 0 to m, then I have what, you just multiply everything by xj, right? So it will be summation I running from 1 to n bj ai x to the power I plus j. Okay, that's how you multiply. But now look at here again. So everything is with element of x, even j0. Okay, j0 for instance, let us write, that might be the only tricky thing, but it's not. J0, that will be, we will have j running from, sorry, I running from 1 to n b0 ai x to the power I. So there is no this term, right? There is no term of constant term. Similarly, I have I running from 1 to n, then I have b1 ai x to the power I plus 1, and so on and so forth. The last one being summation I running from 1 to n bm ai x to the power I plus m, right? So as you can see, there is no constant term at all. Okay, so this particular ideal, in fact, it is okay, I will tell you afterwards. This is actually ideal generated by x. So okay, anyway, we'll see the definition also. Another one is the following. Another one, let's say, now I will take a little bit different example, but very similar. Now two variable, okay, in two variable. So let me consider ideal I1. Okay, so ideal I1 is maybe okay, so typical element, right? So I1 I2 x to the power I1 y to the power I2, and what I want to say is that I1 I2 are natural number, and ai1 I2 are real number. Okay, now same thing, actually I'm doing the same thing as above. Remember, okay, as usual, everything in algebra, what I'm doing is finite summation. Whenever there are summation, there are finite, these are the finite sums. So now again, look at I1 I2 natural number. I'm not allowing them to be I'm not allowing them to be actually yeah, I'm not allowing them to be this thing 0. Okay, but let me modify a little bit. I can allow one of them to be 0, but not both. So I will this such that I1, I2, this is non-zero. Okay, okay, is this clear? That I1, I2 is non-zero comma 0. It cannot be 0 comma 0. That's what I want. So I can have, for instance, I can have I1 comma 0. That is okay. Only polynomial x. I can have 0 comma I2. That is also okay. Okay, but not both. Not both I1, I2 are 0. Okay, that's the main point. Again, you can see it's very easy to verify that again you can see that the I1 under addition is a abelian group of A under addition. Furthermore, exactly the same reasoning as above. Let's say I have fx summation b, let's say j1 j2 and xj1 xj1 and yj2. Now here it is arbitrary polynomial of A, therefore I can have j1 j2 belongs to n union with 0. They can both be 0. It's okay. Now suppose I multiply, let's say px belongs to I1 be such that general polynomial, let me write, this is of the shape A I1 I2 and x I1 y I2, right? This is of this form. Okay, and then of course I can have fx into px, right? So what is it now? This is a summation. Let's say summation over, I will write as a j1 j2 just to make clear that we are summing over I1 or summing over j2. So this is same thing, summing over j1 j2 and then summing over I1 I2. You have b j1 j2 a I1 I2 and then x to the power I1 plus j1 y to the power I1 plus j2. Okay, now same thing here, because remember both I1 I2 cannot be 0. That's the condition for polynomial to be in I1, right? I1 I2 cannot be 0 0, not both are 0. That's the important part, not both are 0. Okay, that's the important part, and therefore this fellow x to the power I1 plus j1 y to the power I2 plus j2, that cannot be 0 for any I1 and any I and j, right? So again you can see that this is in I1. So there is no constant term in this. So you can actually in fact generalize this, but we'll come back to it later. So let me now okay, is there any question? Okay, so let me now define what I mean by ideal generated by something. So okay, definition. Okay, so I will actually for simplicity let me assume A to be commutative. It can be said about general ring also, but we don't have much time, so let me say it is commutative. Okay, so let A be a commutative ring with unity, always with unity. Okay, uh, let okay the non-empty set, okay, let S be a subset, non-empty subset of A. Okay, then the ideal generated by S denoted by S is the following. Now again, just go back, let us go back to the remark I made that the ideals in a ring, where is it? Yeah. Yeah, ideals of ring can be thought in a similar way as a subspace. So actually, in from the linear algebra that what do you mean by subspace generated by bunch of elements, right? What are those? These are the all possible linear combination. Exactly same thing will be here. Instead of scalars, they're scalars, we look at the elements from ring A. So this will be summation. Of course, as always, these are the finite sum AI Si such that AI can be from A, Si are necessary from S, right? And these are finite sum. So maybe I can write it like this. Okay, I running from let's say 1 to n, where n is natural number. Okay, so you can have this thing. Is this clear? So you can basically, it's we are saying that fine, it is a subset. You are given subset. First of all, you make it into group. Okay, how to make it into group? But again, you whenever you have some element from S, its negative has to be there. So how do you get a negative? Just multiply by -1. Okay, you must have seen in a ring the following property that the -1 into S is actually -S. So here, wait, I will rewrite it. So just to recall, you must have seen from the ring that -1, okay, into some element S is in fact minus of S. What does it even mean? So minus one means the additive inverse of unity 1. So that into S will be the additive inverse of S. Okay, so that's the basically what you require. So in this way, you can see again that very similar to what we did for the vector spaces. And now let's go back again to examples above. You can actually see that it's very easy, in fact, to see that this is in fact the ideal generated by single X, because you want to take all possible linear combination of X. That's what we precisely did. But remember also that our here of course there is X square. How do you obtain X square? But X square is in fact X into X, where the first X can be thought in to be a element of ring, and the second X is what the element of set is. Similarly, you can get X cube and so on, and take the linear combination. In a similar sense, this particular one, I1 is in fact ideal generated by two element set XY. Okay. Okay, and in fact, actually, the abuse of notation, we usually write it as by abuse of notation. We simply write. We just forget about the braces. We simply write XY, ideal generated by XY, and similarly above here. Simply write X. Okay. All right. Is there any question? Okay. Fine. Now now that we know about ideals, so let us come back to let us move forward and with the other definition of maximal ideal. Let's first define maximal ideal. Again, I want to because again I don't want to go into left ideal, right ideal, because we don't have much time. So I will again give the definition in the commutative ring. So maximal ideal in a commutative ring. Okay, so an ideal, let's say M in A is called maximal. Okay, first of all, it should be proper, right? So it should not be the whole ring A. That's the first condition. And secondly, if there is an ideal I of A such that M is contained in I contained in A, then either M is equal to I or I is equal to I. Okay, so basically it's maximal with respect to inclusion. And that's what it should be, the ideal, and it should be the maximal with respect to inclusion. So that means proper ideal first of all, and then if I have ideal in between ideal M and A, then it is either M or either A. Okay, is this clear definition? Okay, then I want to give the definition of prime ideal. So an ideal P of a commutative ring, of course with unity, A is called a prime ideal if, again, it should be proper ideal. Okay, proper ideal of A, and second of all, given A comma B in A such that A into B belongs to P, then either A belongs to P or B belongs to P. So it's very similar to the prime number in ring of integers, right? So a prime number, P is a prime number. If it divides A into B, then it either divide A or divide B. It's very similar. Actually, we'll see exact same analog afterwards. Okay, so at least today, let me at least do the following. Just before that, we will prove the existence of maximal ideal. Okay, given any commutative ring, in fact any ring, you will always have a either left maximal or right maximal. Okay, so before that, I will require something called John's lemma. I'm sure that you know this. So can anybody, does anybody want to tell what is a John's lemma? You can unmute and maybe. Okay, so so before that, another definition is the chain. Okay, I will give here only. Let's see. All right. So John's lemma. So okay. So let S be a non-empty, partially ordered set. Okay, so partial order means what? If I have to, okay, it satisfies the reflexivity, right? And anyone? I hope everyone knows the partial order, right? So x is related to x is less equal x. If x is less equal y, y is less equal z, then x is less equal z. Okay, and so on. Okay, so partially ordered set, but what we are saying is in general, if x and y are there, then it may not be true that x is less equal y or y is less equal s. So that's the thing. Okay, so suppose it is partially ordered set. Now suppose in this set, so let T be a subset of S, which is a chain. Okay, what does it mean to say it is a chain? Okay, that is, given x and y in T, suppose you have x and y in T, then either x is less equal y or y is less equal x. Okay, this is called chain. Okay, actually we'll give example. In fact, the proof of the result will kind of example. Okay, so what if we are saying, okay, fine, first of all, it is a non-empty partially ordered set, so there is some order. Generally we write less equal, but just the notation for partially ordered. Okay? And then T be a subset of S, which is a chain. Okay, non-empty. Chain means, so in fact we are saying it is ordered. That means take any two elements from T, then either x is less equal y or y is just some subset, not necessary s itself, right? So you have such a chain. Then what happens? Anyone? So John's lemma says that if every chain T of S has an upper bound, what is upper bound for T means there is element. So what is it? So that is, there exists some S in S such that X is less equal S for any X in T. This will happen for every chain. Okay, for every chain, suppose this happens, if it has, suppose it has upper bound, then S has a maximal element. Okay, so has a maximal element, that's important. You can have multiple maximal element. Remember, it's only a partially ordered set. So we are not saying that everything must be less equal some other thing, or everything is bigger equal some other thing. That's not the case. So that's why we say that there is a max. John's lemma asserted that there is only existence, that there is a maximal element. You can have multiple maximal element. Actually it will be very clear when we now see the proof of existence of maximal ideal. And of course we'll give example where you can have several maximal ideas, right? I'm sure you might already know about it. Okay, okay, is this clear? Okay, so let me give the theorem about the existence. Again, for simplicity, I'm assuming everything to be commutative. So let A be a non-zero commutative ring with unity. Okay, let A be, then A has a maximal ideal. It can have several, but at least one is guaranteed. Okay, so proof is of course via John's lemma. So for John's lemma, let's go back to the proof. You should have a set with partial order, non-empty with partial order. So A is of course non-empty. Yeah, it is a non-zero commutative ring. So of course it has a 0 and 1 distinct elements, so it is a non-empty set. Now with this you want to find ideals, so you begin with, so S to be the collection of proper ideals. Okay, so let's say collection of ideals are A such that A is a proper ideal. Okay, is this non-empty? Okay, this is a collection of proper ideals of A. It is non-empty. Note that 0 ideal belongs to S, and as A is a non-zero ring, that's very important, non-zero ring, that's where the hypothesis is used. We have that 0 is not equal to 1, and this will imply that ideal 0 is proper. Actually, it's very easy exercise. You must have seen that ideal, ring is 0 if and only if the additive identity coincides with the multiplicative identity. So therefore, when a ring is non-zero, we have 0 and 1 are distinct. So of course, that's why the 0 becomes a proper ideal. That's why we require non-zero ring. Okay, so this is a non-empty set. So very good. Then what should be the partial order? Remember the definition of maximal ideal. Remember what we want to show. We want to show that A has a maximal ideal. So maximality, let's go back to the definition. See, this maximal was with respect to inclusion, right? If there is a inclusion of this form, then either ideal I must be I, or ideal I should be the whole ring. So basically that's what the partial order you can have. So what is the order? We say that ideal A, okay, A in S, so we say that A is less equal B if A is subset of B, okay, where that's the partial order you have, where the ideal A and B are from S. So you have proper ideals. Let's say A is less equal B, then when we call it, well, A is subset of B. Okay, so that's what we will do. So again, it is a partial order, as you can see immediately, that if A is a subset of B, B is a subset of C, then of course A is a subset of C, and certainly A is a subset of A. And here you can see that there might be two ideals, they may not be related. That is, one may not be contained in the other. That is all right. So this is only partial order. We say this. This is a partial order on S. Okay. Now, John's lemma says that the very important condition that you have a chain of ideals. Okay. If I have a chain of ideal, then it should have upper bound. Then we can talk about, you can apply John's lemma, right? That is the hypothesis. So how the chain will look like? So consider the chain. Remember, in the chain, by the definition, means every element is related to other element. So therefore, in our case, because we are inclusion, so consider the chain, any chain. Say, AI. Okay, these are the chain such that AI is contained in AJ, either, okay, or AJ is contained in AI. Now we need to find what we need to find, upper bound for such a thing. So of course, the immediately what you can do is that put A to be the ideal A to be the union of AI. Just take the union. Now, because of this very important condition that either one of them is contained in another, you can see that this is an ideal. And in fact, the proper ideal, because everything here is proper. Okay. Yeah, everything is proper. So therefore this is put, this is equal to this, and okay, then this is, then A, okay, I will just write A belongs to S. Okay, the union, because very this you should verify, actually easy to verify, but anyway, worth verification, that this is because of this condition. It's very important. Yeah, so what we have, okay, fine, I have, and because it is union, okay, because it is union, we have AI is less equal to A. So this will imply that A is an upper bound for this thing, this AIs. Okay, AIs, they, fine. Now apply invoke Zorn's lemma. Now all the hypotheses of Zorn's lemma are satisfied. By Zorn's lemma, there exists a maximal element M in S. Okay, and so M is a maximal ideal because of the construction. It is a proper. Remember, John's lemma says it is a element, maximal element in S. That's also S has. So the maximal element is in S. So this S is a what are the elements? These are the proper ideals of A, right? So these are the proper ideals of A. So it is a proper ideal, and it is maximal by thanks to the John's lemma. Okay, is this clear? Okay, maximal element implies that M is maximal. So that's the proof. Is this clear? Okay, any question? All right, so let me example again. All right, so let's look at A equal to Rx, and the ideal that we have seen above generated by X. So will it be maximal ideal? What is your guess? Anyone? So in fact, it will be maximal ideal. Let's see. So first of all, so let A be an ideal of A. Okay, so let's say this is an ideal. Now, what we can do is let F belongs to A be a polynomial of least degree in A. We can choose that, right? Because the degree of a polynomial is integer. So, yeah, well, natural number. So we can always have a polynomial of least degree, because I can take a least element among the natural number. It can have multiple, that is all right. But there is one, that's all. Be polynomial least degree. Now our first claim is that this ideal is actually generated by this thing. Okay, that's my first claim. Now, how to show this? Of course, as usual, there is equality. We have two inclusions. So by very definition, by the definition, what we have, the ideal generated by F must be subset of A. That's clear, because F is already in A, and so any multiple of F must be in A because A is an ideal. right? So therefore, this is clear that this is now the converse part. Suppose let's say G belongs to A. Okay, let's say G belongs to A. Now it's very crucial result. Of course, it's not a difficult result, but very important result, namely division algorithm. By, or you might have seen it as a Euclidean algorithm, whatever. So let me use that by division algorithm. There exist polynomial Q and R where in Rx such that what will happen? I can write G as Qx times f of x plus Rx, correct? And where degree of R is less than degree of f. That's the thanks to division algorithm. Degree is strictly less, the remainder, right? The remainder has degree strictly less. So we have this. Now something interesting happens. Note that f and g are both part of A. That's the assumption. And hence Qx times fx is in A. And because of this, because it is ideal, right? I've multiplied by any element of ring. It should be again in ideal. And therefore, G minus, because it is an abelian group, this fellow is also in A. But what is this? This is actually, that is the polynomial R, the remainder is in A, which is absurd, because remember what was it? F, the choice of F was the least, right? This was a least degree in A. That's the crucial one, least degree in A, right? So therefore, what you got degree, so that is A in A. However, F belongs to A was chosen to be of the least degree. So what is the only possibility? It should be 0. Rx has to be 0. What does it mean? So that is G is written as Qx times F, which is actually the part of F. Yeah, that's the definition. Every multiple of F. That's how the ideal generated by F look like. So we begin with arbitrary polynomial in ideal A, and then we show that it is multiple of F. So hence this will imply that the ideal is generated by F. So very important result, in fact, actually as a part of example I have proved, is that basically what we showed, any ideal of a polynomial ring in one variable will be generated by a single polynomial. So crucial result, right? So given any ideal is generated by a single polynomial. Okay, now we will use this. Now thanks to this claim, now we will show that I1, this ideal generated by X, is maximal. Okay, so that now is very easy. Now suppose, now we show that our X, right, ideal generated by X. Now by the above claim, Okay, there exists some polynomial in A such that, in fact, polynomial in ideal A such that A is actually generated by that polynomial, single one. So this will imply that ideal generated by X is contained in ideal generated by F. What does it mean? In particular, oh, what happened? Screen is frozen. Okay, let me reshare. Can you see now? Can you see now?
Yes, sir.
Okay. Sorry. Okay. Uh, so I hope this you have seen, right? So let me repeat. I don't know when it got frozen, but the claim is that yeah, from the above claim, you take any ideal that contains ideal generated by X, it must be generated by some element F, right? So ideal generated by X is contained in like this. So in particular, this X belongs to ideal generated by F. Is that clear? You can see now, right? Okay, so X belongs to ideal generated by F. What does it mean? So X must be, so that is, there exists, let's say some, yeah, some P in A such that X is equal to P of X times F of X. Okay, what does it mean then? So just compare the degrees. Yeah, you just compare the degrees. So this will imply that, because you know the left hand side is degree 1, the right hand side, what will be the degree? It will be degree of P plus degree of F. So degree 1 is equal to degree of P. So 1 is equal to degree of P plus degree of F. So of course that will yeah, that will tell you, because remember X is a part of F. So this will tell you that in fact F is a multiple R multiple. So F is an R multiple of X, right? Because it's a degree 1 polynomial, right? So that's how it is. Is this clear? Okay. So so that's how we can do this. So this will imply that I think it's again frozen, is it? Let me just close and reshare. Sorry. Just wait a minute. I will reshare a bit. Okay. Can you see now? I hope. Can you see now?
Yes, sir.
Okay. Thanks. Okay. So here it is. So therefore, what we saw is that, well, this is X is, so in particular, X is, so ideal generated by X is maximal. Okay, now to give another example, I will not actually give the whole proof, but it's very similar to what we did just now. Give another example is that consider ring to be integer, ring of integer, then you can show that exactly actually the same thing. Then any ideal of Z is generated by a single natural number, any, let's say non-zero, anyway zero ideal is generated by zero, generated by a single natural number. Okay, and same thing we can do is the following, that an ideal, okay, maybe I will rephrase it, all maximal ideals of Z are of the form generated by P for some prime P.
There your screen is not.
Oh, again problem.
It's is at x equals to p of x into f of x. They don't know.
Oh, I see. Just okay, try again.
Option of this. It's
Can you see now?
yes, sir.
Okay, so let me just repeat. So for a ring of integers, again, what we did actually, the division algorithm works for integers, of course, right? That any same, exactly the same proof. Instead of polynomial, we use the degree, right? So instead of degree, you use the least natural number which is contained in the ideal. The same thing will give you that any non-zero ideal is generated by a single natural number, and all maximal ideals are generated by prime P, some prime P. Every prime will give you maximal ideal. Now here actually you can see that the John's lemma that tells you that there existence of maximal element, so it can have several maximal element. Okay, none of them are comparable to each other, so that is okay. All right, so I have, I think, some 10 minutes. Okay, so let me actually I wanted to give some more example, but let me do something related to quotient ring for that. That's important actually. So before that, even before that, let us consider the ring homomorphism. Okay, so a map, let's say phi, from R to S, a map phi. So both are rings of rings is called a ring homomorphism if, first of all, it's a abelian group homomorphism. Okay, so under addition, right? So we have addition is a group homomorphism. First of all, that's the case, and second of all, I am using the unity in R should go to unity in S. Another assumption that because of unity, I am assuming that we have rings with unity always. So one, that unity of R I denote by 1R should go to 1S. And the third one is actually, it is a monoid homomorphism. That means phi of R, R1, R2 is actually phi of R1 into phi of R2. Okay, for any R1 R2 from R. Okay, this is a definition of ring homomorphism. Okay, I hope you can see, right? Okay, so this is a definition again. To summarize it, basically it says that first of all there are two operations on ring, right? Addition and multiplication, abelian group structure and monoid structure. First of all, when you want to say ring homomorphism, they should respect those structures. What does it mean? As a abelian group, that should be a group homomorphism, and as a monoid it should be group homomorphism. That 2 and 3 is actually monoid homomorphism. So that 1 goes to 1 is very important for us. Okay, so so very easy examples I can give. The standard one. So let me begin with a standard one, that consider n to be, okay, I can be more precise. Let's say, yeah, n to be the natural number, and consider pi from z to z mod nz. What is a map? Well, you take x, consider this. So this is simply the remainder of x after dividing by n, right? So this is a ring homomorphism. Easy to check. Now another crucial one that I will be using actually is, so let some element a in R, 0 or non-zero, doesn't matter, and consider, so evaluation map.
So screen not visible.
Oh, again. Okay. But in between it was, or throughout it's not visible? Okay, let me again share.
So it is the problem for the last 10 minutes.
Okay, I see. Okay, can you see now? Can you see now?
It's okay, sir.
Yeah. So, okay. So, did you see the definition of ring homomorphism? Okay. So, let me consider the evaluation map from EV of A to Rx. You consider the polynomial ring to R. What is a map? Simply that you take a polynomial and evaluate at A. Right? So, for instance, basically, if I have a polynomial like this, then maybe bad notation, I will perhaps use b here. Yeah, so it will go to summation bi a to the power I. Okay, that's how the polynomial map. Is this okay? Is it visible? Okay, so now the thing is that this is ring homomorphism. Now how to show this? The very, okay, under addition, it's very easy to show, right? Evaluation of f plus g is of course evaluate at f at a plus evaluate g at a. That's very clear by the nature of it, right? The way it is defined. The only trouble sometimes happens is for multiplication, right? So let's look at it. So we have, let's say the polynomials, two polynomials, let's say I running from 0 to n, bi x to the power I, let's say this is polynomial f, and let's say g is a polynomial I running from 0 to m ci x to the power m. Now I want to multiply them and evaluate. So evaluation of f into g. So first of all, let's consider evaluation of. So this is summation I running from 0 to n. Then summation, let me call j running from 0 to m bi cj x to the power I plus j. Correct? That's how the polynomial multiplication is defined. Now look at it. So basically, under addition, it's linear, right? And we know that. So therefore, I can use the above. I can use the above to say that it is I running from 0 to n, and then evaluation at a of this polynomial. Okay. I hope it's clear. And again, linearity I will use 0 to n, right? So it is summation j running from 0 to m, and I evaluate at this. So basically, very basically, you can see that the linearity is inbuilt because the way polynomials are multiplied. So therefore, this basically boils down to checking the following. Namely, evaluation of a at x to the power I y to the power j is same as evaluation of x to the power I, sorry, not y to the power j, x to the power j, right? This is same as this, which is actually very easy. Just yeah, look at it, because once you have this, you get back whatever you require because of linearity. This is easy, and result follows from the linearity of evaluation map. Okay. I think it's time, so let me stop here as of today. We'll continue next time. So any questions? Okay, there is some oh, I just got chat. Okay, some questions. So I can see only one now. Okay. To have a maximal ideal for a ring is commutativity must. Okay, no, actually it is not required, but for simplicity I'm assuming you can do exactly same proof. Instead of word ideal, you replace it by left ideal or right ideal, whatever you require. Exactly same thing will go. And there is in the proof where we use the commutativity, okay, I think I just explained it. Yeah. Okay, any other question?
Sir.
Yeah. Sorry, I cannot hear you.
Sir, namaste, sir.
Huh.
Sir, namaste.
Yes.
Sir, every maximum ideal of a commutative ring is a prime ideal.
Sorry.
Sir,
Maximal ideal.
every maximum ideal of a commutative ring is a prime ideal.
Yeah, it's a prime ideal, correct.
Right,
We will show that actually.
Yes, sir. But the converse is not true.
Converse is not true, correct.
So example, so please give an example.
I will give example actually.
Yes,
Next class I'm going to do it. Prime ideals because I have defined, but I haven't given, right? So I will give examples of prime which are not maximal.
Yes, sir. So further,
So because I want actually to go to quotient ring, so basically quotient out with some ideal becomes integral domain but not a field. It is
Yes,
easy to find such examples.
yes, sir. So under question, in the case of bullet ring, every ideal is maximal or not. Everything is prime or not.
No, not every ideal is prime.
So what is the condition for a prime ideal? Ideal to
No,
be
that's
prime.
what. Yeah, prime ideal if and only if I will give the criteria that the quotient, if you quotient out with some that ideal, it should be a integral domain.
Integral. Yes, 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 sir.
Yeah, and
So
for
without-
maximal ideal, quotient should be filled. So that will give you exact criteria.
So without equivalence, is
Sorry,
it is it is a prime ideal if and only if it is without equivalence.
quotient ring is without. Yeah, quotient ring is without this zero divisor. Yeah, in any commutative ring.
In Boolean ring, sir, Boolean ring, what happens?
Sorry,
In a Boolean ring,
I can't hear actually.
in a Boolean ring,
Oh,
every
Boolean ring. Okay,
sir, in Boolean ring, what happens? In the case of Boolean ring,
Boolean ring. What you require? Maximum. Every prime is maximal.
every ideal, the ideal is prime ideal or not. If so, what the
Okay.
condition?
Sorry.
Every ideal, prime ideal or not in a Boolean ring.
In a Boolean ring. So
Yes,
Boolean ring means you want to say x square is equal to x.
yes, sir.
Okay.
Is every ideal in a Boolean ring prime ideal or not?
Okay. Let me think about it. Every okay. Okay. As of now, I have to think about it. I'm directly not sure. I will some do computation and get back to you.
So is there any chance that if it is without typical domain, can it be
Sorry,
a prime ideal?
I can't hear you.
If the Boolean ring is typical domain, then every
Boolean
ideal
ring is integral domain.
is typical domain. Yes, yes. Then every I think is prime ideal comes not.
Sorry, every.
Every prime ideal is every ideal is a prime ideal or not. If it is integral domain.
No, I have to think. I don't know as of now. I have to compute and see. But I think in Boolean ring, prime will imply maximal. Prime and maximal are same. That I can see. But in general ring, every ideal is. I don't think so. But I have to find example.
Okay, sir. Thank you.
Yeah.
Any questions from any analysis? Okay, sir. Thank you so much.
Okay.
Thank you.
Thank you.
All participants, thank you for analysis. Thank you once again, sir.
Yeah. Thank you. So I can log out now.
తీసుకొచ్చా లాస్ట్
సెట్ చేసాం సార్, చెక్ చేసాము. మీకు మార్చాలి, ఒక్క నిమిషం చెక్ చేస్తున్నాం. మేము కనెక్షన్స్ చెక్. హలో. హలో. హలో.
These are the modern
Hello,
Ma'am, in general property.
are you able to hear me?
Video conference.
General settings fund. General settings fund. General settings fund.
Hello, are you able to hear me?
Yes, ma'am.
Okay. Actually, I'm just joining from the two things because otherwise I mean, I write on one of the tablet. So I'll just see whether I can share the slides.
ఒకసారి కెమెరా చూడు అంటే కెమెరా బ్యాక్ కెమెరా
The horizontal three dots. The horizontal three dots.
Okay, for what actually you are
General settings.
setting?
After view to start video, share button is there.
Share. Just one sec. Let me share it. Is this okay? Right? You can able to see it, right?
Yes, ma'am.
Yes.
Drop down to all. Good afternoon to all. I request Sri P. Mahalakshmi Naidu sir from NRC Kakinada to introduce Archana ma'am to the participants.
Good afternoon to all and all. Good afternoon to one and all. Myself, P. Mahalakshmi Naidu, lecturer in mathematics from NRC Kakinada. We are great privileged to have the knowledgeable person, Dr. Archana More with us. She is working as assistant professor at University of Hyderabad, Telangana. Before that, she worked as visiting scientist at Chennai Mathematical Institute. She did her post-graduation at IIT Bombay in MSc Pure Mathematics. She did her PhD under the guidance of Professor N. Raghavendra in August 2004 at Harish Chandra Research Institute, Government of India, Allahabad. Her research focused on algebraic geometry, mainly vector bundles. Under her guidance, one student completed his PhD and two students pursuing their PhD. We enjoyed a lot with her lively and joyful classes and learned so much at University of Hyderabad. For example, all of us, we use the A4 size papers every day, but most of us don't know the ratio of the edges. But the madam explained with just two foldings of A4 size, the ratio is 1:√2. Thank you, madam. Welcoming to session.
Thank you very much for this kind introduction. And thanks for inviting me here. Are you able to hear me, Madhavi, properly?
I'm a little bit problem here now.
Just give me a second, okay? Let me try with this. thing. Hello, are you able to hear me now?
Now it is clear.
Okay, fine. So I'll use the Bose, use my this thing, okay?
You can
Let me
start.
share. Yeah, I'll share. Okay, just 1 minute. Okay. Just give me a second, okay? So today we are going to learn about Silos theorems and let us see what is it. And I'm sure some of you are already familiar with it, so I don't need to really. It is kind of just an introduction, and you can learn more about it from a lot of sources. I'll give you those sources, okay? And for instance, if I want to study Silos theorem, or if I want to teach Silos theorems, it required lot of time, because you need to know about group actions. You need to know about uh, more about application part and so on. So at least it needs some 4 to 5 sessions. But today we only have a one session. So what I'm going to do is I'm going to introduce you what are Silos theorems are, and some examples we will do. Proof of Silos theorems are very interesting, but for that we have to do group actions, and not everybody is familiar with group actions. So I don't want to go into proof of it, and I'll see whether I can discuss applications. Otherwise, I'll just give you the notes where or some material where you can discuss about. You can read about applications and so on. Okay, so I'll just start what are Silos theorems, about Silos theorems. So Silos theorems are mainly, it came because of, in fact, Silos proved these Silos theorems because of Lagrange.
Ma'am, just a second, ma'am. Some people have problem, ma'am. Can you please increase your voice, ma'am?
Oh, increase my volume. Okay, wait a second. Hello, one sec, let me see the settings, okay. Okay, I don't know. It is at the maximum. It is at the maximum, so I don't know what to do. Are you able to? If I talk loudly, is it okay?
I think we are in some analysis they have problem.
Okay, is there any way I can do that? I don't know. Everything is okay. Hello. If I talk loudly, is it okay? Hello. Hello. Me. If you, I don't know what to do about this.
Give me
In the
a second.
platform also, we are not able to hear you. Am I not audible? Hello, Madhavi. I'm not at all audible, is it? Shall I try with other? Speaking device.
Ma'am, just give me a second.
Okay, fine. Is it directly if I talk, is it okay?
No, ma'am.
Means I'm right now using a speaker of computer, not this.
Ma'am, you can continue.
Okay, fine. I'll try to talk loudly and let us see how it works.
Okay, ma'am. Thank you.
So, what I wanted to tell was Silos theorems. Silos theorems are mainly to tell what is the converse of Lagrange theorem. Actually, I think I'm able to hear the sound from. It is possible to mute something. Hello.
Ma'am.
Yeah. Yes, Madhavi. Yeah. Shall I continue? I'll continue now. I think this is okay. I'm not hearing any echo sound. Yeah. So, Silos theorems are mainly for the purpose of to prove the Lagrange converse of Lagrange theorems. Okay. So, for example, converse of Lagrange theorem is false. That all of us know. And real example for that is A4. So, what is the order of A4 is? If order of A4 is 12, that all of us know, right? Because what happens is S4, A4 is a normal subgroup of A4. A4 is a normal subgroup of S4 consisting of all the even permutations. And since we know that order of S4 is 24, order of A4, we know that there are exactly 12 even permutations and 12 odd permutations, and order of A4 is 12. So now we know that 6 divides 12. Now, what is the Lagrange theorem is? It is about whenever we have a subgroup, order of a subgroup divides the order of a group. Now we are asking converse part. That means if there is a sum number which is a divisor of order of a group, can we have a subgroup which is of that order? So for instance here for 12, 6 divides order of a group A4. So now we are asking a question, is there a subgroup whose order is 6 in A4? That is what is our question is. And if you recall, if you look at here A4, I listed all the elements of A4. What are the elements of A4? They are either, these are the even permutations. So if you take a product of 2 of the transposition, that will give me an even transposition. So 1, 2, 3, 4, 1, 3, 2, 4, 1, 4, 2, 3. These are the four cycles of type 2, 2, what we call is as this. So these 4 elements are there along with identity. Plus we have, if you take any cycle which is of even order, even length, then its order becomes odd. And if it is of odd length, then its order becomes even. So for example, here 1, 2, 3, if you look at this is a 3 length cycle, and this is a even cycle. So this will also belongs inside A4, and such a 8 3 cycles are there with us. So totally we have these 3 cycles which are totally, there are 8 3 cycles are there. Then we have this product of 2 transposition, these are 3 are there, and identity. So totally in E4 we have a 12 elements. Now we can see this E4 little differently also. That means we can actually see E4 as group of symmetries of tetrahedron. Okay, so let me actually show it to you. Let me see if I can actually show it to you. So Can you see here tetrahedron? Tetrahedron means you have a totally 4 faces. Okay, this is different. Can you see here? 1, then this is a pink color, then we have a yellow color, then we have this green color and this, okay, it is the same red color. So these are the 4 faces of tetrahedron. And what I want to do is I want to find out what are the symmetries of these things. Okay. So what we are doing is we are actually giving a vertices a number. So this is, for instance, vertex 1, 2, 3 and 4. So we have a 4 vertices. And what we want to see is we want to see the symmetry of this. Okay. So how to see symmetry of this? We have to essentially find out what is the axis where all the other elements will be fixed and things will be smoothing. So for example, let us look at here. So what is happening over here in this first figure? We have this, our axis of rotation is passing through 4. So suppose if we call this as a 4 and then we are putting one axis which is actually coming to the center of this other equilateral triangle, which is the face. Okay. And then what we can do is we can rotate them. Okay. So if I rotate here now, what is happening is this vertex is 1, 2 and 3. Right. So if I rotate around this, how many permutations I'll get? I'll get these 3 permutations, right? One is identity, which that means we are not moving anywhere. Then we rotate. That means what will happen is this 1 will go to 2 and 2 will go to 3. So that will be the 1 permutation, right? But this is not enough. I can do actually 2 times. So what is going to happen is 1 goes to 3, then 3 goes to 2. That is the another permutation. So here we can look at A4 also as a symmetry of tetrahedron. Okay. So all these 1, 2, 3, 1, 3, 2, 1, 2, 4 and all of this. So what about 1, 2, 4 means what is happening over here? 3 is the one which is fixed. So suppose this is my vertex which is 3. So third vertex, if I want to make this as a fixed vertex, what I'm going to do is I'm going to pass axis through vertex third and the center of my equilateral triangle over here, the face over here, and I'll put this thing and then I'll rotate it around this. Okay, so what is happening is now 3 is being fixed and then 1, 2 and 4, these vertices are interchanging among themselves in the rotation form. Okay, so that is these are the ones which are going to take care of these 3 cycles. Okay. Now, but these are not the enough permutation. What other permutations we can give is, suppose if I take a midpoint of this line and a midpoint of a line which is opposite to it. Okay. And if I join them together. So if you look at these permutations, so what we are doing is we are looking at a midpoint of one of this edge and you look at opposite of that edge, and then what you do is you look at the midpoint of these 2 edges. Now, if you pass through your axis of rotation over there, and if you rotate now, what is going to happen is if you see the rotation along this, what is going to happen is this one will go to 2 and this 3 will go to 4. Okay. So now we have totally we have totally 6 edges are there. So likewise, there will be 3 pairs of opposite edges to each other, and they will give me precisely these 3 permutations. Okay, you understand this? You look at a midpoint of this edge, and then you look at a midpoint of this edge. Pass your axis of rotation through there, and then actually what you do is you rotate it, and you will notice that precisely this part will go to this part, and this part will go to this thing will go to this thing, because this is the axis of rotation, and this thing will interchange themselves. Okay, so this is my A4. Okay, so A4 you can do, you can see it as a 2 ways. One way of saying A4 is you just look at it as an even permutation within A4. S3, you look at it as like that, or you can actually look at it as the group of symmetry of tetrahedrons. Okay, these are the 2 ways of interpreting A4. So now once I have a A4, what we want to see is we want to see that there exists no subgroup of A4 which is of order 6. Okay. So in order to prove that, what we have to do is, so suppose if it is let us look at it as a proof by contradiction, and suppose H is a subgroup of order 6. Now if you look at H, which is a subgroup of order 6, what happens to its index becomes 2, right? So once this index becomes 2, that means we all of us knows that any subgroup of order index 2 is normal. So because of that, H will become normal. And then if I take a quotient, so we all of us knows that if you have a group G and if you have a normal subgroup N inside my group G, then what happens is G quotient out by N, this becomes group. In fact, this is a if and only if condition. So if H is any subgroup such that G quotient by H is a normal, is a group, then in that case, that subgroup becomes normal. So this is if and only if condition. So now this becomes a group. And whenever we have a quotient group, what we have is we have actually a quotient map. So this from A4, I can define this quotient map to A4 quotient out by H. Okay. So here what is the quotient map is X goes to H cos H. Now what is the order of my A4 quotient out by H is 2. And what we know, whenever we have a finite group of given order, then if I take any element and if I square that, if I raise that element to that particular order, it becomes identity. So since order of my this group is 2, what I know that XH whole square, this is going to be identity. Identity in the quotient group is same as that of a saying H, right? So what is the meaning of this thing is, this means is H square of H is equal to H. And this will imply that X square belongs to H. Okay. So what we are saying is that we are saying that for every X belongs to A4, X square will belongs to my this group H if such a group exists. Okay, that is what is our conclusion is. But now there is a problem. What is the problem is in A4, what are the elements? So in A4, I have this element which is of order 1, 2 and 3, right? I mean, these kind of cycles we have. Now what happened to this cycle? We know that cube of this cycle is equal to identity, right? Because these are 3 cycles, their order also is 3. So now if I take a 1, 2, 3 raised to 4, which is actually 1, 3, 2 square, this will be, this is same as that of a 1, 2 and 3, right? So what we are doing is we are starting with a 3 cycle 1, 2, 3 and I show that 1, 2, 3, this is the square of 1, 3 square. And just now we have seen that for every X belongs to A4, X square belongs to H. So this will implies that 1, 2, 3, this is an element of A4. So what we have shown that, and in fact there is nothing special about 1, 2, 3. You take any 3 cycle I, J and K. I know that I, J, K is same as that of a I, K and J square. So it is going to belongs to, sorry, this is wrong. This is belongs to H. Okay. So what we are saying that all these cycles, they belongs to H. So if all the 3 cycles, they are element of H. So now if you look at how many 3 cycles do we have totally 8 many 3 cycles are there, right? So now 8 number of elements, they are already a subset of H and order, and I know that cardinality of H is equal to 6. Certainly this is not possible, right? So that means what we have proved it, such a H doesn't exist, okay? So, so here we can see that if you look at the Lagrange's theorems, converse is not true because in A4 we don't have any subgroup of order 6, okay? So now, groups and so on, they are being studying for many years now in, across the world. So people have started studying what happens, may not be the entire converse may not be true, but what one can check is whether partial converse is true or not. Okay. So what do you mean by partial converse? Either you put a condition on your group and in that case, Lagrange's theorem is true, or may not be all subgroups of given divisor belongs there, but it is possible that some of them may be inside your group. Okay. So for so there are some of these theorems are already there. Okay. So what are those theorems? For example, Cauchy's theorem. What is Cauchy's theorem says that if I have a group G, so what Cauchy's theorem says that if I have a group G and if there is its order is divisible by some P where P is a prime number. Okay. So if I have a group G whose order is divisible by prime number P, then in that case, what happens is there exists an element of, so there will be X belongs to G such that X raised to P is equal to identity. Okay. So once I have such an element, what I have is I have a group which is subgroup which is generated by X. That means X square up to X raised to P. You're able to see my slides, right? I mean, is it big enough? If you have something, you can unmute and tell me, okay? If you're unable to see the slides, or if you have any question also, you can unmute and say. So if I look at this is a subgroup whose, of G whose order is going to be P. So what Cauchy's theorem says that it is not always possible that for the given divisor D, you can have a subgroup of that order. But what Cauchy's theorem says that if that divisor is a prime number, then in that case we can always able to find one subgroup of order P. At least one subgroup of order P. There could be many more. That is, he's not saying, it is just giving a existence of at least one. Okay. Now, then another, I mean, there are some more theorems are there which I did not list it over here, but I'll just tell you. Suppose if you have a group G whose order is P to the power K, where P is any prime number, okay? And remember that in these cases, we are not assuming our group to be abelian group, okay? Whenever it is abelian group, converse of Lagrange's theorem is true. I'll tell you that. But I'm saying that suppose if I take a group G whose order is P to the power K, like for example, if you take a Q8, okay? What is this Q8 is? It is this group of quaternions. So this group is given by, its order is 8 and its elements are given by plus or minus 1. Plus or minus I and plus or minus K and plus or minus J. Okay. So if you look at this, you have this I, J and K, and their multiplications are defined I into J is equal to K, and if you go in the reverse direction, you will get a minus sign. Okay. So this is a non-abelian group of order of, but it is of the form 2 to the power 3. That means 2 is a prime number. So it is so such a kind of groups we call it as a P groups. Okay. So what is P group means? A group G whose order is P to the power K for some prime number K are called P groups. Okay. So even we have a result that if you have a P groups, then for every P to the power I, which is a divisor of G, you will have a subgroup of that order. Okay. So that means Lagrange theorem is also true for for a P groups. Okay. That is also we have. And then another thing, so here what we are doing is we are putting a constraint on the order of a group. Okay. Here we are actually, the converse is not, it is a partially true because we are saying that not all divisor, but for a given prime divisor, you will have a one element. But in case of G is a finite abelian group, then what happens is, then Lagrange's entire converse is true. That means if you have a divisor, if you have any divisor M divides N, then there exists a subgroup H of G such that cardinality order of H is equal to M. Okay. So entire converse is true if your group is abelian. So these are the partial results which were already known. Okay. But sometimes these partial results are not enough to classify groups. Okay. So what do you mean by classification of groups? Classification of group means, suppose if I give you an order of a group, how many different types of groups are there? What do you mean by type? That means up to isomorphism. Okay. So for example, all of us knows that, I'll tell you. So what do you mean by classification? So classification of group in the sense what I am saying is, suppose if I give you a order of a G is equal to N, how many different groups are there which are non-isomorphic to each other? Okay. So what we are doing is we are doing up to isomorphism, how many groups of that orders are there. Okay. That is called classification. Okay. So for instance, if I take all of us knows that if you have a group of order 4, then there are then that group is always going to be abelian group. That we know. Another thing we know about it is if you have a group G, then that group will be isomorphic to either Z4, that means it is a cyclic group, or it is of the form Z2 cross Z2. Okay, so here actually let me fix my notation. So Z4 means what? Actually I'm actually taking 0 bar, 1 bar, 2 bar and 3 bar, but I won't be writing this bar, so I'll denote them by 1, 2 and 3. Okay, here what is this thing is? This group is 0, 0, 0, 1, then I'll have a 1, 0 and then I'll have a 1, 1. Okay, so all the group of order 4, they will be divided into two types. One is the one which is isomorphic to Z4, or other is the one which is isomorphic to Z2 cross Z2. Similarly, if you look at if you take order of a group to be 6, then in that case also we have only two groups which are isomorphic, non-isomorphic. One is non-abelian group, which is S3. It is a permutation group of 3 symbols, and another group is Z6. Again, it is a cyclic group of order 6. So classification in that sense. Okay. So what we want to do is we want to classify all the groups of given order. And this problem, there are many people for the many years now, more than probably, I don't know, 200 years, they are, may not be 200, but at least 150 years, they are working on classifying different groups of different orders. And believe me, this problem is very difficult. Okay, so given any order, I mean like even 200 or something which is lies between 200 to 300, if that number is given to you, it is not all classification of a groups is not known. And there are many people who are working in that kind of research. Okay. So, and then in all these classification theorem, the first step is the Silos theorems. Okay, so let us actually, I'm keep on talking about silos. Let us actually see what is this Silos theorem is. Okay, so a Norwegian mathematician, Peter Louis Silo, in 1872. So I'm saying you, I mean, this result is also very old. Okay, nowadays, whenever we actually present a results, they are much more. I mean, if we are presenting something, we are generally present something which is much more recent. But you see the Silos theorem, they came in 1872. So this paper was published in Math Annales, French journal, and he discovered that a converse result is true when D is a prime order. Okay, so what is the meaning of that thing is, let G be a finite group if P is a prime number. So such that P to the power K divides order of a G, then G must contain a subgroup of order Pk. Okay. So here what we are seeing is that, so Cauchy's theorem, if you remember what Cauchy's theorem was telling, Cauchy's theorem says that if P divides order of G, then there exists a subgroup of order P. But here actually we are generalizing that result. What we are saying is that for every order P to the power I which divides the order of a G, you will have a subgroup. Okay. Indeed, if you look at the proof of Silos theorem, what we generally prove is, we prove that if order of G is equal to P to the power K times M, where M and P is co-prime with each other, that means what we are doing is we are taking out the highest power of P to the power K lies inside my order. Okay. So P to the power K is kept aside, and rest of the things, there is no multiple of P is there. Okay. So then in that case, what we prove that? We prove that there exists a subgroup P of order P to the power K, which is so sorry, there exists a subgroup P such that cardinality of order of P is equal to P raised to K in G. Okay. And then as I said that every P group is converse of Lagrange's theorem holds for every P group. So since this is a P group, you will have all the P to the power I, which will be a subgroup inside P. And once it is a subgroup of P, it is going to be a subgroup of G as well. Okay. So if you prove that, so in order to prove this theorem, what we have to prove is, we have to prove that there exists a subgroup whose order is P to the power K. Okay. So this is what is and this is what Silos proved. Okay. So now and not only that, what he also proved is, which is also very important, that suppose if P and Q, these are two Silos, two subgroups are there whose order is P to the power K. Okay. Then he proved that there exists a relationship between this P and Q. And what is that relation is? They are conjugate to each other. What do you mean by conjugate to each other? That means there exists some G belongs to G such that GPG inverse this is equal to Q. That means if you have two subgroups whose order is the maximum power of P, which divides order of a group, then in that case they are conjugate to each other. Okay. So this theorem is quite nice because of the following thing. Suppose in case you prove that order of a, I mean, if you show that there exists only one silo P subgroup, then we know that it is a normal subgroup. Okay. And once it is a normal subgroup, what happens is, you know the definition of simple group, right? So what is the simple group says? Simple group means a group which doesn't have any subgroup which is a non-trivial subgroup. That means it is not a trivial or not a G, which is a normal. So such a group we call it as a simple group. So Silo's theorem many times we use in order to prove that certain theorems are certain groups are not a simple groups. Okay, that means there exists this normal subgroup there. See why normal subgroups are important. Existence of normal subgroup or non-existence of normal subgroup is important because of induction step. Okay. So what happens many times in group theory, we I mean we use all of us knows that mathematical induction is a very key technique which we use throughout all the areas of mathematics, right? All the disciplinary of mathematics, we will be using induction. So in order to use the induction in group, what happens is, suppose if I take a group G and suppose if H is a subgroup of G, many times what happens now, certainly if H is a proper subgroup of G, then what will happen is we can use the induction hypothesis, right? But induction hypothesis to go from here to here, this gap to fill up, we have to look at this quotient group G by H. But as all of you know that for any H, G by H may not be a group, right? Be a group. Okay. So in this case, what we need is we need this H to be a normal subgroup. Okay. Then only it is possible. So Silo's theorem many times help us to give such a existence of that non-trivial normal subgroup inside group G. Okay. And I'll actually share the source, but there are big mathematicians which are telling you that Silo's theorem, we use it in, so many places that we don't even know. So it is like when in analysis, when we take real numbers and we say that any interval will have a rational number or rational numbers are dense there, right? So many times we use that fact very frequently. Similarly, Silo's theorems are also used in that frequency in group theory. When problem comes to classification, when problem comes to using the inductions, we will be using Silo's theorems. So this knowing Silo's theorems is very important, and I think it should be an integrated part of our mathematics graduate program. Now we have this 4-year of graduate program, right? So in that we should be teaching these kind of techniques because they are really integrated part of a group theory as a subject, as a research topic. It's very important. Okay. So let us see, before going into the proof of it or before even stating the theorem, let me give you example. Okay. So what are we saying over here? I'm saying that if G is a group, I'm saying that there exists a subgroup with the highest power of P, which divides order of a group, and there exists such a group. Let us actually first find out whether it is really true or, of course it is true, but let us see some examples. Okay. So, so let me just quickly tell you a small thing. So what we are saying is that suppose if my order of a G is 100, then what is 100? 100 is 2 square into 5 square, right? So here there are two prime numbers which are involved. One is 2 and another is 5. 2 and 5, right? So what Silo's theorem guarantees us that there will be a subgroup of order 2, there is a subgroup of order 4, there is a subgroup of order 5, and there is a subgroup of order 25. So these guarantees is given because of Silo's theorem. Okay. But it doesn't give you guarantee that 2 into 5, which is equal to 10, there is a subgroup of order 10. We do not know about it, okay? So it just says that we have a group of order 2, we have a group of order 4, we have a group of order, subgroup of order 5, we have a subgroup of order 25. So for example, let us look at inside A4. Anyway, I'll be working on that, but let me just quickly see. So what is the order of A4 is? Let me just clear this part. Okay. So if you see in this example, what is happening over here, order of A4 is 12, which is 2 square times 3. So here prime numbers involved are 2 and 3. These are the two prime numbers which are involved. Okay. So now what Silo's theorem says that there exists a subgroup of order 2. There exists a subgroup of order 4. And there exists a subgroup of order 3. See, at this point, generally I ask questions and then we can discuss the answer. It is much more nicer if we interact, but because of this online thing, let us just, we cannot do that. So apologize to, please apologize to me that these sessions are not becoming interactive. I hope sometimes I'll physically present and give these lectures, then we can actually interact and then we can make these lectures more effective. So currently it is like a one-way conversation. Really sorry for that. But let us see here, okay? So what we are saying is that a subgroup of order 2. Okay, so what is the subgroup of order 2 over here? If we look at all these elements, what is these elements are 1, 2, 3, 4 of this type, okay? If I take a square of these, what will happen is, this will be 1, 2, 3, 4 into 1, 2, 3, 4. And what we know about cycles, if cycles are disjoint, then they commute with each other. Okay, so these I can put it here and I can push it here. So I'll get a 1, 2, 1, 2, 3, 4, 3, 4. So this is 1, 2 square and this is 3, 4 square. So which is identity. Okay, so all these three elements, this one, this one, this one, these three elements will give me 3 subgroup of order 2. Okay. What about subgroup of order 4? If you collect all these elements, 3 of them together, that will give me a subgroup of order 4. And indeed, you have seen it, all of them have order 2. So because of that, it is going to be isomorphic to Z2 cross Z2. Okay. What about a group of order 3? Group of order 3, it is a prime power, right? So because of that, any element which is of whose order is 3, that will give me this group. So all these all these 3 cycles are there whose order is 3. So because of that, they will contribute to the subgroup of order 3. But if you look at this 1, 2, 3 and 1, 3, 2, they will be in the same subgroup. So you will have a subgroup identity 1, 2, 3, 1, 3, 2, and similarly others. So you will have such a 4 subgroups are there of order 3 in A4. Okay, so this is what. So though order 6 group we do not have, we have a subgroup of order 3, subgroup of order 4, and subgroup of order 2. That's what Silo's theorems actually guarantee also, and we have verified over here. Okay, so so that is about this. So now let me give you a definition of what is the Silo subgroup. Okay, then it will be easier for us to use it. Okay, so let G be a finite group and if P is a prime number, a subgroup G whose order is the highest power of P dividing order of a G is, so what we are saying is that a subgroup of G whose order is the highest P which divides order of a group G, this is called P Silo subgroup. Okay, there are some other notions also, people also call it Silo P subgroup. So if you see Herstein book, then he call it as a Silo P subgroup and not a P Silo subgroup. But we can use any of this terminology, and in this particular lecture I'm going to use P Silo subgroup as a okay. And any P Silo subgroups are called Silo subgroups also. Suppose if I want to say that there exist Silo subgroups, that means it could be in A4, if you look at in A4, you have different types of silo subgroups. Okay, so this is for the simplicity of using. I don't need to keep on now repeating saying that group of order something and all that. I can just say simply say that silo 2 subgroup or 3 silo subgroup and so on. Okay, so let us see some examples of order 12 groups. Okay, so there are 5 types of 5 isomorphic, non-isomorphic groups are there of order 12. Some of them, let us quickly see what are the silos, silo subgroups are. So when you look at the order of a group is 12, it is 2 to the power 2 square and 3. So we will have either 2 silo subgroup will be there or we will have 3 silo subgroup. Okay. These are the two silo subgroups will be present here. 2 silo subgroups, whose order is going to be 4 and 3 silo subgroup will have order 3. Okay. So let us see the simplest example of group of order 12, which is Z12. Z12 means what? It is a cyclic group of order 12. Okay. So you will have an element all like this. Now in this, remember that whenever we have a cyclic group, you will have a unique group of that order. Okay. So like for example, in 12, if I have a 4 divides 12, so you will have a unique subgroup of order 12 and it will be generated by element which is suppose if 1 is a generator, it will be 1 to the power 3, but this is additive group. So we have to add, 3, right? So this is the one which will be generated for that group. So if I want to look at those 2 silo subgroup in Z mod Z12, I'll have only one subgroup which is generated by 3. Okay, so this is my 2 silo subgroup inside Z12. 3 silo subgroup is the one which is again what we have to do is 12 divided by 3 is equal to 4. So we have to look at a subgroup which is generated by 4. So subgroup which is generated by 4 is 0, 4 and 8. Okay. So this will give me a unique silo 3 subgroup and this will give me a unique silo 2 subgroup. Okay. So now this is one of the abelian group, but there is another abelian group of order 12. What is that group is? What is that group is which is isomorphic to which is non-isomorphic to Z12 and which is abelian is Z2 cross Z6. These are the only 2 abelian group will be there in when you are looking at order 12. Okay. So 2 silo subgroups are so 2 silo subgroups are inside this. So 2 silo subgroup will be of order 4. Okay. So this is, if you look at here, see, remember that this is now Z2 cross Z6. Okay. So we won't have one element of order 4. Like for example, here, any cyclic group, its subgroup is also going to be cyclic, right? But this group is not a cyclic, so we don't have any element of order 4. But what we have is we have an element of order 2, 2 and 2, 3 of them. And if you collect them together, they will give me a group, okay? So if I take, for example, 0, 0, what is the order here? Anyway, this is unit. What about 0, 3? If I add 0, 3 plus 0, 3, this will be 0, 6, but 6 is 0 over here, so this is 0, 0. So its order is 2. Okay. Similarly, 1, 0, if I take it, 1, 0 plus 1, 0 is 2, 0. Now, so now what is happening is I have this 2, but 2 is inside this Z2, so I'll get a 0, 0. Okay. Similarly, if I look at 1, 3, it will be 1, 3 plus 1, 3 is going to be 2, 6. This is 0 over here. This is 0 over here. So I get a silo 2 subgroup which is given by Z2 cross Z2. I mean, which is isomorphic to Z2 cross Z2, which is generated by these elements, and subgroup of order 3. This should be 3. Okay. Now what is this? This is wrong. Sorry. It should be 3. Oh, sorry, this is correct, sorry. So as I said in silo theorem, what it says that if any prime power divides it, so for example, 4 is there, so 2 also is there, right? So if I look at a subgroup of order 2, they will be, each of them will be generated by this element because all of their order is 2. So these are this set, okay? And silo 3 subgroup is unique over here again, and that will be generated by, see, in Z2 we do not have any element of order 3. So because of that, Z2 won't contribute anything for this subgroup. So I'll only have a 0, 0, 0 in this. And there is only one element which is actually inside Z6, which will give me a subgroup of order 3, which will be generated by 2. So I'll have actually this 2, 4, 0. So this will be a silo 3 subgroup. And remember that yeah, in between I mentioned that if you have a 2 silo subgroups, they will be conjugate. What happens to them? They will be conjugate to each other. Now, if you look at abelian group, conjugate to each other means what? If you take, since it is abelian group, nothing will be conjugate to each other except for itself, right? Because if I write a GP inverse, since it is abelian, it is same as that of a P. Okay, so because of that, since if you have a two silo subgroups, they will be conjugate to each other, they will be equal. Okay, so in non-abelian, in the abelian case, when I have a silo subgroups, they will be unique. Okay, so for example, in two silo subgroup is only, this is the only possibility. If you try any other subgroup, there won't be any other subgroup of order 4 other than this. In 3 silo subgroup also it is going to be unique, which is only this one. You don't have any other silo 2 subgroup or 3 subgroup. Okay, so remember that in abelian group, any if you take a power which is a maximum power of P, which divides your group, then there will be only one subgroup of that order. Okay, right. Okay, so this explanation I suppose is enough for us. Now let us see what happens to the other example, which is A4. Okay, so in A4 we have already seen, so let me not waste our more time on this. So this is, as I said, these are the okay. Now another important group of order 12 is D6. Okay, so what happens to D6? D6 means actually our notation. Let me fix it. D6 is, one is a rotation, R raised to 6 is identity, and another is S, where S square is equal to identity. Okay, so and it is given by this relation, R raised to 6 is identity, S square is equal to identity, and R into S is equal to S into R raised to 5. Okay, this is the relation. Actually, in general, our relation we write it as a RS is equal to S R inverse. But we know that R raised to 6 is equal to identity, so R raised to 5 is the R inverse. So I wrote it as a R5. Okay, right. So now in these groups, in this group, if you look at how many 2 silo subgroups are there, this is a non-abelian group. Okay, so it is possible to have a many more silo subgroups. You can have multiple. Okay, so 2 silo subgroups in this, they are given by this one R cube S R cube into S. Okay, we see once we have, remember that all of them are isomorphic to Z2 cross Z2. So if I give any 2 elements, it is enough, and both of them should have an order which is 2. So all the elements which are of order 2 are S is there, then RS is there, R square S is there. I mean, there will be 6 elements of order 2, but they will be also splitting, right? I mean, when I'm looking at a group. Okay, and then this we have R3, which is a rotation, and I know that R raised to 6, which is equal to identity. So R cube is also of order 2. So all the 3 subgroups which are 2 silo subgroups are R cube 3s, this one and this one. Now remember that in A4 we have only unique silo 2 subgroup, right? See, when we want to say that two groups are not isomorphic, these kind of things are also okay. Like for example, why A4 is not isomorphic to D6, you can say that there is only one subgroup which is a normal inside A4 of order 4, but on other hand in D6 you have a 4 silo subgroups, and what we know also that they are not even normal, because once they are 3, we know that they are different conjugate to each other, right? And once they are conjugate to each other, what happens is normality will be lost, because what is the normality means G inverse is equal to P for all G belongs to G. Okay, but we know that all of these are conjugate to each other, so because of that they are not normal. Okay, so you can say that E4 has one subgroup of order 4 which is normal, but D6 doesn't have, so they are not isomorphic. Okay, And if you, but in D6, we have only one subgroup, which is of order 3. And since it is a one silo subgroup, unique, it is going to be normal. Because what we know that if you look at any conjugate of them, they will be, all of them has to be order 3 and they will be the same. Okay. So this is a normal subgroup of D6. Okay, so now actually let us move to little bigger order, which is 24. Okay, so so what are the subgroups of order 24? The one which is well known to us is S4. Okay, so S4 is of order 24. So, and if you recall what is S4 is, S4 will be consisting of these, they are all the permutation of order 4, right? Of symbol, 4 symbols, 1, 2, 3, 4. So now and always remember that permutation, it is always better to write them as a cycles. Okay. So what are the types of cycles which are possible inside the 4 symbols are only, one is 4 cycle, 1, 2, 3, 4. Another is this 1, 2, 3, 4. So what is happening is it's a product of 2 transposition. Another is just a transposition, and last one is 3 cycles, 1, 2, 3. Okay. So now how many 4 cycles we have? So for this, actually what we do is we formalize this following. So one has, so the first position, it has a 4 choices, right? Second positions, we have a 3 choices. Third position, I'll have a 2 choices, and fourth position, I'll have 1 choice. But now 1, 2, 3, 4, this cycle is the same as that of, instead of writing 1, I can write it as a 2, 3, 2, 3, 4, 1. And I can same way, I can write it as a 3, 4, 1, 2, or I can write it as a 4, and then I will write it as a 4, 1, 2, 3. All these 4 of them are unique. I mean, they are the same cycle, okay, same cycle. So because of that, we can divide it over here, and I'll know that there are only 6 cycles which are of the type 1, 2, 3, 4. Okay. For this product also, what happens is I had to only choose 2, and then the rest of the 2 will be fixed. So to choose this 2, what is my formula here? It is a 4 into 3. And but then what we know that if I take a 4 into 2, either I choose a 3, 4 or I choose a 1, 2. Both of them will give me the same cycle. So I have to divide it by 2. And also 1, 2 is the same as that of a 2, 1. So I have to divide it by 2 again. So what I'll get it? I'll get a 3 mini cycles. So these are these 3 numbers. If I want to choose a transposition 1 and 2, I don't have that interchanging part, right? So what I have is I have a 4 into 3 divided by 2. So I'll have a 6, right? This will have 4 choices, this will have 3 choices, and I have to divide it by 2. So I'll have a 6 mini. And for the 3 cycles, you can use the same kind of a trick. What is this? For 1, I'll have a 4 choices. For 2, I'll have a 3 choices. For 3, I'll have a 2 choices, and I have to divide it by 3. So I'll get 8 cycles. So this is my complete picture of S4. Okay. So if I want to study S4, what I have to study is I have to study all these type of cycles. And remember that A4 is a normal subgroup of S4. And what we know that if I choose any 2 cycles of the same type, so if I choose any 2 cycles in this set, if I to choose any 2 cycles in this set or this set or this set, they are going to be conjugate to each other. And whenever I have a normal subgroup, conjugacy class, this is essentially a conjugacy class. Okay. So those who knows about conjugacy class says what is the class equation. So class equation of S4 is in fact 1 plus 6 plus 3 plus 8 plus 6 plus 8. This is actually a class equation of S4. Okay. So and A4 is a normal subgroup of it. So remember that whenever that whatever that conjugacy class, entirely it has to go into that set. So if you look at here in A4, it has actually this entire class and this class. These 3 class together is A4. Okay, so A4 is a normal subgroup of this S4 because of this. Okay, so now anyway, so let us look at what happens to in the S4. So in S4, we again 24 is what? 24 is just a 24 is what? It is actually 2 to the power 3 times 3. So I'll have a 2 silo subgroup will be there, and I'll have a 3 silo subgroup. But now in 2 silo subgroup, I have a order to be 8. No longer the order is 4. Okay, in A4 we had a 2 silo subgroup of order 4. But now in S4 you will have a two-sided subgroup is of order 8. Okay, and it is interesting that all these all these two-silo subgroups, they are isomorphic to D4. Okay, that means they will be the what is that? They will be essentially all the symmetries of our squares. Okay, and those are given by, if you look at this 1, 4, 3, 2. So you look at, sorry, I generally write like this. So it is 1, 2, 3, 4. And then you actually look at all the permutations. So what happens is D4 acts on these, and whatever permutation I'll get, those permutations will give me a one subgroup. So let me explain it to you. What is the meaning of this thing? So if I take this 1, 2, 3, 4, I want to see how D4 acts on this. So what will happen? So first action will be rotation, right? So rotation will give me 1, 2, 3, 4, right? Now one rotation means it is a rotations with a 90 degree, right? Now what I can do is I can actually do another 90 degree. So in that case, one will now won't go to the second place, it will go to first. I mean, it will skip 2 and it will go to the next place. So it will go to 3. But what will happen to 3? 3 will skip 4 and it will come to 1. So I'll have a 1, 3. Similarly, what will happen to 2? 2 will skip 3 and it will go to 4. And 4 will skip 1 and it will go to 2. So I'll get this thing. Okay. If I do actually now the rotation with a 270 degree, then in that case, 1 will skip now 2 and 3 both and it will go to 4. And now 4 will skip 1 and 2 and it will go to 3. Then 3 will skip this 4 and 1 and it will go to 2. So I'll get this. So likewise, if you write it down, this is the subgroup which is given by this. This is a subgroup which is given by this. And this is a subgroup which is given by this and this. Okay. So these are the three subgroups in S4 which we get it. Okay. And it is very interesting if you give this kind of example to students that just because of D4, I have a 4 copies of D4 inside S4. And remember again, this is not a normal subgroup because whenever I have a silo subgroups which are more than one, we know that they are conjugate to each other. Okay. Once they are conjugate to each other, what I know that they cannot be normal, because for normal subgroup what happens is they should be conjugate to only itself. It cannot be conjugate to other. So in if you look at 4 silo subgroups in S4, they are not normal. Them is normal and they will be given by this. Okay. Now, similarly, if you look at 3 silo subgroups, they will be all given by whatever are subgroups of A4, they will give me a 3 silo subgroups. Okay, I won't spend much time on this. Let us go to the another example. Okay, so group of 24, that there is another subgroup is there which is of order 24 and it's quite important. Okay, what is this group is? This group is it is called SL2Z3. Okay, so SL2Z3 means what? S is stands for special, L is stands for linear. So it is called special linear group. And 2 is, I mean, all these groups are consisting of 2 cross 2. I mean, 2 means it is a 2 cross 2. If SL3 means it will be 3 cross 3. So I have this 2 cross 2 matrix is over here. And then I have this Z3. So that means entries are coming from Z3. Okay. So Z3 we are going to denote it by 0, 1 and -1 like that. Okay. So, and what is the special about it is its determinant is 1. So I directly wrote it AD minus BC is equal to 1. Okay. So what we are doing is we are looking at all the matrices which are 2 cross 2 matrices. Each of the entry is coming from Z3 and its determinant is 1. So first place, let us see how many elements are there. Of course, I wrote it here that it is 24. So it should be 24, but let us see whether it is 24. Okay. So, see, when I have a subgroup, when I have a matrix whose first place is determinant is not equal to 0, right? So if I look at this first column, it has to be non-zero vector, right? Unless and until it is non-zero vector, I can't do much. So, and how many such a non-zero vectors we have? So A can have a 3 possibilities and B can also have a 3 possibilities. But among these possibilities, A and C, both of them will be 0. That is also a one possibility which is counted. So I should exclude that possibility. So I'll have a 8 vectors which are non-zero vectors here. Okay. So that means I'll start with the 8. Then what about B? B I can actually give anything. So B can be 0, 1, 2. Okay. So it is having a 3 choices. Okay. So now, but what about D? See, once now what is happening is A, C and B, all these three entries are fixed. So now let us see what happens to D. So D times A minus BC is equal to 1. Okay. Now BC, A, all of these are fixed numbers. Okay. So because of that, D doesn't have any choice among itself. Okay. Actually, there is a little bit I should have done it in two different cases. Like for example, if A is not equal to 0 and then C is, and when A is equal to 0, these two cases if we do it is much better. But anyway, for since we have a time constraint, let me not go into detail. But when you are calculating, you do it into two steps. Okay, whether one is 0, A is non-zero. Okay, but essentially you can see from this equation that D doesn't have any choice. So because of that, number of elements which will be determined by A, C and D, and it has totally 24 choices. Okay. So once I have this, so because of that, this SL2Z3, it has totally 24 elements. Now what happens is, whenever I have any matrix A, I know that if I multiply by identity, this is the same as that of A times identity, right? That means this identity is always inside a Z center of SL2Z3, right? All of us agrees, right? Now, if I multiply I2 by minus 1, then what will happen if I take a minus identity times A? This is also going to be A times minus identity, right? Because this will be minus A and this will be minus A. So, I2 minus I2 also is an element of SL2Z3. Now, if you remember, S4, center of S4 is a singleton identity. Okay, only identity is element is there inside center. It doesn't have non-trivial center at all. So now, so because of that, what we can claim that? We can claim that SL2Z3 is a different, it's not isomorphic to S4. Okay, that is the case. And interestingly, if you look at this SL2Z6, here I actually listed all the elements over here. If you look at, actually I listed it exactly like the way I counted. So for example, you look at here, this is my first vector is fixed. Okay. Then what did I do? This has three choices, 0, 1 and minus 1. Can you see this? 1, 0. So I only have a 0, 1 and minus 1. These are three choices are there. And once I have these three choices, this number is automatically going to be fixed. Okay. Similarly, here also what did I do? I fixed this one and then actually I'll give you one calculation. For instance, let us look at here. So if 1 minus 1 is there and 1 I fixed here, I want to calculate what is the value of D. Okay, then what I can do is D minus D plus 1, this has to be equal to 1 because we want determinant to be 1, right? So D will be automatically 0. Okay, so once I fix these three entries, this entries is going to be fixed. So let us again see this particular example. So in this, what is there? Minus 1, minus 1, minus 1 and D. Let us see what value of D I get. So I get a minus D is equal to minus 1, this is equal to 1, right? So what I get it? I get a minus D is equal to 2. So D is equal to, but 2 is what? It is minus 1. So D is equal to 1. So you look at here. Okay. These are simple calculations. Okay. Now, if I want to calculate what is the silo 2 subgroup of this, so 2 silo subgroup of this is order is going to be 8. Okay. And here you have to do explicit calculation. Okay. It is little bit, what you call, you have to work on this. So in this case, what happens is, if you look at all the orders of each of these element, you will only find 8 elements whose order is either 2 or 4. So remember that in if I have a group of order 8, all the elements which are going to be of order either 2, 4 or 8, right? So in this case, what happens is it's these are the only I listed over here. This one, this one, this one, and this one. These are only 8 elements are there whose order is either 1, 2 or 8 or 4. Okay. And if you notice this, if you look at here, each of these element, if I take a 1, minus 1, I, minus I, j, minus I and j, this group is actually isomorphic to Q8. Okay. So, so only subgroup which is inside SLZ3 is of order 8 is only 1. So this is a normal subgroup. This is the first observation. SL2 Z3. And as I told you that in S4, you don't have any subgroup, any normal subgroup of order 8. You don't have. There is no. Okay. But in SLZ3, you have a one normal subgroup of order 8. Okay. So this is how actually, it has a fourth 3 silo subgroup of order 3, that means 3 silo subgroups, and they are essentially listed over here. So as I said, what did I tell you that? I told you that when what Silo's theorem says that given a highest, I mean, whatever is the power, highest power of that P, you should have a subgroup. That's what we illustrated now in all these examples. Okay. So let me at least, I have another 20 minutes. So let me state Silo's theorems and we will verify certain things. Okay. So what are the Silo's theorems? Silo's theorems are consisting of various parts, and people also give in a different what people do is actually they write it in a different ways, but more or less these are the versions which we use. And Silo also, what Silo did it, of course he did not say that it is a Silo subgroup, but he just said that it is highest power of P divides and so on. So, but this is more or less thing. I generally split it even further. Actually, I write this as a Silo 4 subgroup also, but the notes which I am using it's called it as a Silo these 3 theorems. So let us see what are they. Okay. So first Silo theorem says that a finite group G has a Silo. A finite group G has a Silo P subgroup for every prime P, and each P subgroup of G lies in some of the P Silo subgroups. So let me explain it again. So let me take a cardinality of G is equal to P to the power K times M, where M and P, they are co-prime to each other. Okay. So what is this theorem says that? Its theorem says that there exists P, which is a subgroup of G, such that order of P is equal to P to the power K. Furthermore, what it says that? It also says that if I is some number for which P to the power I is divides G, then there exists H subgroup of G such that order of H is P to the power I. Okay. And it further says that there will be some P Silo P subgroup, P Silo group, such that H is contained in H is a normal subgroup. Okay. So it says that H is contained inside another Silo P subgroup. Okay. So it is essentially classify all the P groups of P subgroups of group G. Okay. That is what Silo first theorem says. And we have seen it just now, right? We have seen all of these examples, and if you look at those examples, essentially we can verify the Silo 1 theorem. Okay. Now, Silo 2 theorem says about, this is also very important, what it says that for every prime number P, Silo P subgroup of G are conjugate to each other. This is also very important theorem, statement. What is it says that if P and Q, these are two P Silo subgroups, then it says that P is equal to GQ G inverse for some G. And if you see this statement, we use it very often. Okay. That in fact, this part actually we prove sometimes using this part also. Okay. Now, Silo 3 statement is used again really often because it is essentially gives you a classification. Okay. So what it says is, it says that NP, suppose if NP denotes the number of Silo P subgroups. Okay. So we are denoting P Silo subgroup. How many are there? Okay. So what we are saying is that MP divides M. This is very important. Can you see this? So whatever that remaining M, which is that co-prime number to G, we are saying that this NP, number of Silo P subgroups, okay, number of Silo P subgroup divides M. This is very surprising, okay. And we also says that NP is congruent to 1 mod P. So these two statements, they actually contribute a lot to the classification in order to prove that there exists unique unique silo subgroup, or there are various things where we are using this. Okay, we use it many times, and in fact, if you see, even in for the students, these theorems are important even for the purpose of exam point of view. Also, it is important, as well as I said, at a research point of view, classification. This is one of the key point. Okay, and lastly, this is also important that NP is equal to G. So this NP number is, so you fixed one P silo subgroup, then you look at the normalizer of P. Okay, what is normalizer of P means? We are collecting all the G belongs to G, for which G inverse is equal to P. Okay, so sometimes it is possible that our silo P is subgroup, it may not be a normal. In that case, this will be actually, it may not be the entire G. Okay, certainly what we know that P is contained inside normalizer of P. Okay, this is we know, so its scatter, it is going to be more than P to the power K. But what we are saying is that precisely NP is equal to G times NP. Okay, the index of this NP. So this is also, this is a silo 3 star, or sometimes we also call it as a 4. Okay, so these are the 3 silos theorems. So essentially, whenever you are looking at this statement also, you can see that it gives you a classification, right? It gives me certainly existence of some subgroup of given order. It also tells me that when two subgroups are going to be conjugate, it also, what it does, it is actually takes some subgroup, it can put it into another subgroup. That also it tells. It also tells you that how many number of subgroups are possible. Okay, so all of this information actually allows us to do the classification, right? Because we can say that, okay, just by looking at numbers, here we are not looking at a group at all. What we have is, we only have a numbers. By looking at those numbers, we are actually concluding something. It is very amazing because we are familiar with numbers for maybe more than 400 years or 500 years back. We know all these numbers. So their divisors, their prime factorization, all these things are we are knowing. But groups are something which is much more complicated. All of us knows that abstract notions are always very difficult. And then just by looking at those numbers, we are concluding much more things about that group. So it is kind of a very amazing that such a kind of theorems are exist. And when we have such a numbers, we can actually classify our groups much better way. Okay. I mean, I'm keep on talking about classification, but always remember that it is one of the application for the silos. But there are many other applications of silos theorems are also there. Okay, so I'm just telling you about these things. Okay, so now actually let us see the illustration of silo 1 theorem and silo 2 theorem. Okay, so what is silo 1 theorem says us that. So for example, whatever example we have so far discussed, so if I have a group A4, its size is 12. Suppose if my P over here is 3, then H is suppose 1, 2, 3, okay? And K is 1, 2, 4. So what is this? H is generated by this identity 1, 2, 3 and 1, 3, 2. Okay, what is K is? It is 1, 2, 3, 4. Now what we want to, what Silo's theorem says that, Silo 1 theorem says that if I have a 2 Silo P subgroups, so here we have a 2 Silo 3 subgroups, they should be conjugate to each other. Conjugate to each other means what? I need to find a G, which is the element of my A4, such that G at G inverse should be my K. So if you checked over here, what is this? So 2, 4, 3. Then I have this number 1, 2, 3, right? 1, 2, 3 and inverse of 2, 3, 2, 4, 3. What is the inverse of 2, 4, 3 is 2, 3, 4. Okay, we just shift these things. And if you remember, when we do the multiplication of cycles, we go from right to left. Okay, so here what happens, where 1 goes, 1 is not present over here, that means 1 is constant over here. Here what happens is 1 goes to 2. And where 2 goes to 4. So 1 will go to 4. Now we have to look at 4. So 4 here is going to 2. 2 is going to 3 over here and 3 is going to 2. So this goes to 2. Now you look at 2. Actually, after this you can stop, but let me just check it. I mean, why I said that you can stop it? Because we know that whenever I do the conjugation, if I have a 3 cycle, it should be 3 cycle only. It cannot be a 4 cycle. But let us just verify. So here what is happening is 2 goes to 3. 2 goes to 4. 4 is not present over here, and 4 goes to 3. So 2 goes to, no, what I need to check? I need to check 2 where it goes, right? 2 goes to 3 over here. 3 goes to 1 over here, and 1 is not present. So 2 goes to 1 over here. And if you look at 3, 3 goes to 4, 4 goes to 3. So 3 is constant. So I get a 1, 4, 3. And this is the element of K over here. Similarly, if you look at this calculation, it will be 1, 2, 4, which is again an element of K. So what we have shown over here, we have shown that if I have a 2 silo 3 subgroups, then they are conjugate to each other. So this is one of the example. Of course, you have to see there are totally 4 silo 3 subgroups are there for A4. On all of them, you can actually check this. Okay. Another example is D6. In D6, what we have is we have a order 12 is there, and we have a 2 silo subgroups are there. So 2 silo subgroup will be of order 4. They will be, suppose if I have R3S and I have R3RS, then easily you can see over here that R square is the one which is the conjugation. Okay. So what is the conjugation means? I have to look at H, and what I have to do is I have to check that if I product with this element R square, I should get a K. So for example, let us look at over here. So I have an element S, so I can multiply by R square over here, and I have to multiply by inverse of R square. R square inverse is R raised to 4, because R raised to 6 is identity, right? So R square into R raised to 4 is equal to 1. So I have this. Now what happens is whenever I interchange these, what happens is minus sign comes, right? So it is R square into R of R minus 4 S. But R minus 4 is what? It is actually a minus 2, okay? But overall this is R minus 2 times S. R minus 2 is R raised to 4 times S. So I get this, which is precisely if you multiply these two elements, you will get R raised to 4 times S. Okay, similarly this thing if you see, okay, so what we are trying to show that we want to show that if I have a 2 silo subgroups, they are conjugate to each other. So that's why this example. Similarly, I'm not calculating it, but if you look at in S4, what we have is you look at 2 silo subgroups, that means 8 order group. They were actually generated by, they are isomorphic to D6, right? So something is isomorphic to D6, D4. They are isomorphic to D4. And whenever it is isomorphic to D4, it will be generated by 2 elements. One is of order 4 and another is of order 2. So this is this order 4 element and this is order 2 element. And if you look at this, this will give, you can actually do this calculation. Okay, I'll actually encourage you to do the calculation. Okay. And in this 24 SL2Z3, you will have 3 silo subgroups. Their order is going to be 3. And if you look at these two, you will have these as a conjugation. Okay, again, just a simple calculation you can check. Okay, and now actually let me quickly illustrate to check silo 3 subgroups. Okay, so silo 3 subgroups says what? NP divides something and something, right? So suppose if order of G is 12, then you have P is equal to 2 or P is equal to 3, right? These are the only two possibilities we have. Now NP divides 3, and what is the other thing is N2 should divide whatever is the leftover, right? So remember that, or so here 12 is equal to 4 into 3. So this is going to be my M. Okay. So N2 should divide 3 plus N2 should be common to 1 more 2. Now I have only two choices. So here actually this says that N2 is odd, is okay. So and N2 divides 3, it tells me that it can be either 1 or 3. Okay, so if you see our previous example, whatever we have done it, either we will get a 1 silo 2 subgroup or we will get a 3 silo 2 subgroups in all those examples. Okay, you look at here actually. Let us see. Right, so in D6, what we got it, we got a 3 of these silo, these are, there are 3 silo subgroups. There are right, 3 silo, 2 silo subgroups. Okay, so number is 3 and 2 silo subgroups, means group of order 4. Okay, similarly other examples also we can check it. Okay. Okay, if you actually check that thing, and similarly, if you look at N3, in N3 should divide 4 and N3 should be counted to 1 mod 3. In general, what happens? What are the divisor of 4 is? They are 1, 2 and 4. But in this, if you look at, we also need to check that N3 should be congruent to 1 mod 3. So 2 is get cancelled because we do not have actually 2 is not congruent to 1 mod 3. Okay. Similarly, in 24 also what happens is here there is no change. And here we have a 1, 2, 4, 8. These are the divisors of 8. But still, what I know that only 1 and 4, these are the numbers which are congruent to 1 mod 3. So only possibilities for 3 silo subgroups are either 1 or 4. You cannot have actually 6 mini, 8 mini or something like that. Okay, remember that. And this is the table. Okay. So actually I only have a 4 minutes. I don't think so I can do the application right now. But for example, one of the key things which I generally teach to my students is, if you look at a 1 to, all the groups up to order 59. And plus what we want is they are simple. Okay. So what is the meaning of simple group means? G is called simple if only normal subgroups are trivial or G. Okay. So as I was talking to you about this induction step, right? So we generally do induction step for simple groups. Once you do it for simple groups, it is like those prime numbers kind of things. Okay. So simple groups are essentially the building block for our groups. So if you have something known about the simple group, it is much more easier for us to work with it. Okay. So now what we are saying is that if you look at all the groups of order 59 and what are the simple group in that, then only possibles are all of them are abelian first place. And once I have a group G which is abelian and it's simple, just now what we have seen it, Lagrange's theorem is actually true for abelian group, right? So if I have an abelian group, then and we don't want any normal subgroup to it. And we know that for every divisor, I'll have a one subgroup. And any subgroup of a abelian group is going to be a normal. So because of that, if I want a group G to not to have any normal subgroup, what I need is I need order of G to be equal to P. Okay. So if you look at up to 59, only subgroups which are simple, they are only a group of order prime and hence they are abelian also. So if you want to prove this result, we do actually by calculating 1, 2, 3, 4, if given order, why it is not simple. And if you look at like that, what happens is you keep on using Solo's theorem in different ways. Okay, using that we prove this result, and then we also prove that first simple group which is non-abelian is E5, which is of order 60. And for these also, in order to prove this result also, what we have to do is we have to use Solo's theorems. Okay, I'll stop now. I only have 2 minutes, so I don't want to go in detail. And what I'll do is now I'll actually give you a material which is from where I chose this source. So I'll give you that source thing as well as I can actually share these notes. So I'll stop now, and if you have any doubt, I'm happy to take them. Madhavi, maybe you can take over. If you have any doubts, maybe you can ask me right now. Yeah.
From NRC Kakinada.
I'm unable to hear you.
Speak now. Good evening, madam.
Yeah, thanks. I'm able to hear you. Yeah.
You have delivered an excellent picture on
converse of Lagrange's theorem is not true by giving an excellent example. That is F4 of S4. Taking the example F4 of S4. So thank you very much, madam, for giving an excellent explanation. And also silent groups 1 to 3, 4, 1 to 3. And also you mentioned Cauchy's theorem and Nodal theorem on the partial converse of Lagrange's theorem. So in that context, I would say that converse of Lagrange's theorem is true in the case of cyclic groups, I think.
Yes,
madam?
yes.
Yes, madam?
That is true.
Yes, madam? Okay.
Yes.
So, next one, I want to know that every cyclic group is abelian.
What every?
Every cyclic group is abelian.
No. Every silo group you are talking about?
So, madam?
What is the question?
Cyclic group, madam.
Cyclic group is abelian. Yeah, that is.
Abelian, madam. So converse is not true. Converse is not true. Abelian group is not cyclic.
Converse for cyclic group is true. That is correct.
Madam?
Converse of for any abelian group, converse means if you take a cyclic group is abelian. So if you have any order which divides the order of a group, you will have a subgroup. In fact, it is unique also.
Yes, madam. Converse is not true. Converse. So what example? Sorry, simple example. Converse example.
In cyclic group, Solo's theorems are true. What you call Lagrange's converse is true. So I won't have a counter example there.
Converse is not true, madam. Every group is not cyclic. Every group is not cyclic.
Oh, you are asking every abelian group. No. Sorry, that is correct. If you take a Z2 cross Z2, for instance, let me write it. Okay, 1 sec. Actually, sorry, I did not understand your question. Yeah, I'll just give you 1 sec. Okay, just give me a second. Okay. Right. So, for example, if you take a Z2 cross Z2, right? This is a not cyclic group. Okay. Or if you take a Z3 cross Z6, this is also not cyclic. Are you asking this question or did you ask something else? These are abelian groups, but they are not cyclic.
Not cyclic, yes. So under simple example, madam, simple example, any example?
I mean, for abelian case, these are the only examples. Now, I mean, all the abelian groups, they will be of this form only. See, there is a structure theorem for abelian group. What it says that every abelian group, whether it is finite or non-finite, it is going to be isomorphic to z to the power r into zn1, zn2, and znr. So these are all the, I mean, what we call it as a finite rank. So if you put that condition, all group G, they will be of all abelian group will be of this form. And this particular part, we call it as a torsion. Okay. And for this Lagrange theorem is true. Converse of Lagrange's theorem is true.
Madam, both roots of unity is cyclic, madam. Cyclic.
Which one?
Both roots of unity.
Yes, they are cyclic, that is correct. But their rank is not, okay, that's what I said. This is up to certain things. For instance, here, I'm talking about a finite rank, what we call it, okay? If you look at a partition of, I mean, when you collect these unities, right, are you talking about this, right? UR means all the x's belongs to C, such that xi to the power r is equal to 1. And then you are taking union of UR. Are you talking about this example? Are you talking about this example? Are you talking about this part, unity or this one are you talking about?
I don't understand, madam.
What is your question? I'm not understanding actually.
Yes, madam. Yes, madam.
I'm saying that all the finite rank, what we call it, those kind of abelian group, they will look like this. And if you have a group of finite, see, Silo theorems are always given for the finite groups, okay, whose order is finite. So for if you have a finite abelian group, then the Lagrange's converse is true for abelian group. Okay, this is true. So you cannot find counter example in abelian cases at all.
Okay, madam.
Okay.
Thank you.
If you are looking at an infinite abelian group, then actually you can constrain yourself by something called finite rank, what we call. If you look at these kind of examples, or even you can take another example like Z2 cross Z infinitely many times, product of them.
Okay, madam.
So these are the examples are used for the various other purposes, but these are not finite rank thing, but they also are very nice examples. You can do a lot of things with them.
Okay, madam. Thank you.
Okay. So can I leave now, or I mean, we have another session on 22nd, right?
Yes.
Okay.
I think we can close this session.
What?
I request the remaining analysis. If you have any queries, please ask. Remaining analysis? No, ma'am. I think we can close the session. Thank you, ma'am.
Okay, thank you very much for inviting me, and it is nice. Okay, we'll meet on 22nd again. Huh?
Yes, ma'am. Thank you. The next session will be Archana ma'am's next session will be on 22nd. Now 3:45 to 5:15 session will be handled by the resource persons. Offline session. Thank you.